coming on an off day. This is CS50, and before we do a proper beginning today, just wanted to call out a member of CS50's team who's been with us for the past several years, works in media services on campus, and is just one of a whole team of artists that help make CS50 and other classes here on campus possible, and particularly on our audio team here from the ESS group at Harvard. We have a team that helps modulate the audio, raising and lowering things, playing the tunes as we come in, making sure that everything coming out of these laptops sounds great, and particularly as the number of people ebbs and flows in a class, they too kind of hang on those every words to make sure that everything ultimately sounds great. And sadly, one of our longest team members is leaving us and leaving Harvard, moving on to bigger and better things. And just on behalf of CS50's whole team, just wanted to thank Luke for spending so much time with us over the past several years. I know you're not expecting this, Luke, but if you're comfortable coming up on stage, we have a CS50 hoodie for you as a small token of thanks. And given that Luke has pretty much sat in these lectures like 3 times over the years at least, we also have an honorary I took CS50 shirt for him as well. Thanks so much. Now, in just a moment, what you see on the screen is going to be distilled into just this. But give us a moment just to reset here before we dive in. Breaks and such if you have questions. All right, this is CS50, and this is already week 6. And this is the week in which you learn yet another language. But the goal is not just to teach you another language for language's sake. As we transition today and in the coming weeks from C, where we've spent the past several weeks, now to Python, the goal ultimately is to teach you all how to teach yourselves new languages. So that by the end of this course, it's not in your mind the fact that you learned how to program in C or learned some weeks back how to program in Scratch, but really how you learned how to program fundamentally in a paradigm known as procedural programming, as well as with some taste today and in the weeks to come of other aspects of programming languages like object-oriented programming and more. So recall, though, back in week 0, Hello World looked a little something like this. And the world was quite simple. All you had to do was drag and drop these puzzle pieces. But there were still functions and conditionals and loops and variables and all of those kinds of primitives. We then transitioned, of course, to a much more arcane language that looked a little something like this. And even now, some weeks later, you might still be struggling with some of the syntax or getting annoying bugs when you try to compile your code and it just doesn't work. But there, too, the past few weeks, we've been focusing on functions and loops and variables, conditionals, and really all of those same ideas. And so what we begin to do today is to, 1, simplify the language we're using, transitioning from C now to Python, this now being the equivalent program in Python and look at its relative simplicity, but also transitioning to look at how you can implement these same kinds of features just using a different language. So we're going to see a lot of code today, and you won't have nearly as much practice with Python as you did with C, but that's because so many of the ideas are still going to be with us. And really, it's going to be a process of figuring out, all right, I want to do a loop. I know how to do it in C. How do I do this in Python? How do I do the same with conditionals? How do I declare variables and the like? And moving forward, not just in CS50, but in life in general, if you continue programming and learn some other language after the class, if in 5, 10 years there's a new, more popular language that you pick up, it's just going to be a matter of Googling and looking at websites like Stack Overflow and the like to look at just basic building blocks of programming languages, because you already speak, after these past 6+ weeks, you already speak programming itself fundamentally. All right, so let's do a few quick comparisons left and right of what something might have looked like in Scratch and what it then looked like in C, but now as of today, what it's going to look like in Python. Then we'll turn our attention to the command line ultimately in order to implement some actual programs. So in Scratch, we had functions like this, say hello world, a verb or an action. In C, it looked a little something like this, and a bit of a cryptic mess the first week. You had the printf, you had the double quotes, you had the semicolon, the parentheses. So there's a lot more syntax just to do the same thing. We're not going to get rid of all of that syntax now, but as of today in Python, that same statement is going to look a little something like this. And just to perhaps call out the obvious, what is different or now simpler in Python versus C, even in this simple example here? Yeah? Good. So it's now print instead of printf. And there's also no semicolon. And there's one other subtlety over here. Yeah, so no new line. And that doesn't mean it's not going to be printed. It just turns out that one of the differences we'll see is that with print, you get the new line for free. It automatically gets outputted by default, being sort of a common case, but you can override it, we'll see ultimately too. How about in Scratch? We had multiple functions like this that not only said something on the screen, but also asked a question, thereby being another function that returned a value called answer. In C, we saw code that looked a little something like this, whereby that first line whereby that first line declares a variable called answer, sets it equal to the return value of getString, one of the functions from the CS50 library, and then the same double quotes and parentheses and semicolon. Then we had this format code in C that allowed us with %s to actually print out that same value. In Python, this too is going to look a little bit simpler. Instead, we're going to have answer equals getString, quote unquote, what's your name, and then print with a plus sign and a little bit of new syntax. But let's see if we can't just infer from this example what it is that's going on. Well, first, missing on the left is what? To the left of the equal sign, there's no what this time? Feel free to just call it out. So there's no type. There's no type like the word string, which even though that was a type in CS50, every other variable in C did we use int or string or float or bool or something else. In Python, there's still going to be data types today onward, but you, the programmer, don't have to bother telling the computer what types you're using. The computer is going to be smart enough, the language really is going to be smart enough to just figure it out from context. Meanwhile, on the right-hand side, getString is going to be a function we'll use today in this week, which comes from a Python version of the CS50 library, but we'll also start to take off those training wheels so that you'll see how to do things without any CS50 library moving forward, using a different function instead. As before, no semicolon, but the rest of the syntax is pretty much the same here. This starts, of course, to get a little bit different, though. We're using print instead of printf. But now, even though this looks a little cryptic, perhaps, if you've never programmed before CS50, what might that plus be doing? Just based on inference here. What do you think? Yeah, so adding answer to the string hello, and adding, so to speak, not mathematically, but in the form of joining them together, much like we saw the join block in Scratch, or concatenation was the term of art there. This plus sign appends, if you will, whatever's in answer to whatever is quoted here. And I deliberately left a space there so that grammatically it looks nice after the comma as well. Now, there's another way to do this, and it too is going to look cryptic at first glance, but it just gets easier and more convenient over time. You can also change this second line to be this instead. So what's going on here? This is actually a relatively new feature of Python in the past couple of years, where now what you're seeing is, yes, a string between these same double quotes, but this is what Python would call a format string, or F string. And it literally starts with the letter F, which admittedly looks, I think, a little weird. But that just indicates that Python should assume that anything inside of curly braces inside of the string should be interpolated, so to speak, which is a fancy term saying substitute the value of any variables therein. And it can do some other things as well. So answer is a variable, declared, of course, on this first line. This F string then says to Python, print out hello, comma, space, and then the value of answer. If, by contrast, you omitted the curly braces, just take a guess. What would happen? What would the symptom of that bug be if you accidentally forgot the curly braces, but maybe still had the F there? Yeah, it would literally print hello, comma, answer, because it's going to take you literally. So the curly braces just kind of allow you to plug things in. And again, it looks a little more cryptic, but it's just going to save us time over time. And if any of you programmed in Java in high school, for instance, you saw plus in that context too for concatenation. This just kind of makes your code a little tighter, a little more succinct. So it's a convenient feature now in Python. All right, this was an example in Scratch of a variable, setting a variable like counter equal to 0. In C, it looked like this, where you specify the type, the name, and then the value with a semicolon. In Python, it's going to look like this. And I'll state the obvious here. You don't need to mention the type, just like before with string. And you don't need a semicolon. So it's a little simpler. If you want a variable, just write it and set it equal to some value. But the single equal sign still behaves the same as in C. Suppose we wanted to increment counter by 1. In Scratch, we use this puzzle piece here. In C, we could do this actually in a few different ways. There was this way. If counter already exists, you just say counter equals counter plus 1. There was the slightly less verbose way where you could say, let me do the first sentence first. In Python, that same thing, as you might guess, is actually going to be almost the same. You just throw away the semicolon. And the mathematics are ultimately the same, copying from right to left via the assignment operator. Now recall in C that we had this shorthand notation, which did the same thing. In Python, you can similarly do the same thing, just no need for the semicolon. The only step backwards we're taking, if you were a big fan of counter plus plus, that doesn't exist in Python, nor minus minus. You just can't do it. You have to do the plus equals 1 or plus minus or minus equals 1 to achieve that same result. All right, how about in Python 2? Here in Scratch, recall, was a conditional, asking a silly question like, is x less than y? And if so, just say as much. In C, that looked a little something like this, printf and if with the parentheses, the curly braces, the semicolon, and all of that. In Python, this is going to get a little more pleasant to type too. It's going to be just this. And if someone wants to call out some of the obvious changes here, what has been simplified now in Python for a conditional, it would seem? Yeah, what's missing or changed? So no curly braces. And sorry? And we're using the colon instead. So I got rid of the curly braces in Python, but I'm using a colon instead. And even though this is a single line of code, so long as you indent subsequent lines along with the printf, that's going to imply that everything, if the if condition is true, should be executed below it until you start to unindent and start writing a different line of code altogether. So indentation in Python is important. So this is among the reasons we've emphasized axes like style, just how well styled your code is. And honestly, we've seen certainly in office hours, and you've seen in your own code, sort of a tendency sometimes to be a little lax when it comes to indentation, right? If you're one of those folks who likes to indent everything on the left-hand side of the window, yeah, it might compile and run, but it's not particularly readable by you or anyone else. Python actually addresses this by just requiring indentation when logically needed. So Python is going to force you to start indenting properly now if that's been perhaps a tendency otherwise. What else is missing? Well, we have no semicolon here, of course. It's print instead of printf. But otherwise, those seem to be the primary differences. What about something larger in Scratch? If an if-else block like this, you can perhaps guess what it's going to look like. In C, it looked like this, curly braces, semicolons, and so forth. In Python, it's going to now look like this. Almost the same, but indentation's important. The colons are important. And there's one other difference that's now again visible here, but we didn't call it out a second ago. What else is different in Python versus C for these conditionals? Yeah. Perfect. We don't have any parentheses around the condition, the Boolean expression itself. And why not? Well, it's just simpler to type. It's less to type. You can still use parentheses. And in fact, you might want to or need to if you want to like combine thoughts and do this and that or this or that. But by default, you no longer need or should have those parentheses. Just say what you mean. Lastly, with conditionals, we had something like this, an if, else statement. In C, it looked a little something like this. In Python, it's going to get really tighter now. It's just if, and this is the curiosity, elif x greater than y. So it's not else if. It's literally one keyword, elif. And the colons remain now on each of the three lines. But the indentation is important. And if we did want to do multiple things, we could just indent below each of these conditionals as well. All right, let me pause there first to see if there's any questions on these syntactic differences. Yeah? Between what and what? Good question. Is Python sensitive to spaces and where they go? Sometimes no, sometimes yes is the short answer. Stylistically, though, you should be practicing what we're preaching here, whereby you do have spaces to the left and right of binary operators that they're called. Something like less than or greater than is a binary operator because there's two operands to the left and to the right of them. And in fact, in Python, more so than the world of C, there's actually formal style conventions. Not only within CS50 have we had a style guide on the course's website, for instance, that just dictates how you should write your code so that it looks like everyone else's. In the Python community, they take this one step further, and there's an actual standard whereby you don't have to adhere to it. But generally speaking, in the real world, someone would reprimand you, would reject your code if you're trying to contribute it to another project if you don't adhere to these standards. So while you could be lax with some of this white space, do make things readable. And that's Python's theme, for the code to be as readable as possible. All right, so let's take a look at a couple of other constructs before transitioning to some actual code. This, of course, in Scratch was a loop, meowing forever. In C, the closest we could get was doing something while true, because true never changes. So it's sort of a simple way of just saying do this forever. In Python, it's pretty much the same thing, but a couple small differences here. The parentheses are gone. The colon is there. The indentation is there. No semicolon. And there's one other subtle difference. What do you see? True is capitalized just because. Both true and false are Boolean values in Python, but you got to start capitalizing them just because. All right, how about a loop like this, where you repeat something a finite number of times, like meowing 3 times? In C, we could do this a few different ways. There's this very mechanical way where you initialize a variable like I to 0. You then use a while loop and check if I is less than 3, the total number of times you want to meow. Then you print what you want to print. You increment I using this syntax or the longer, more verbose syntax with plus equals or whatnot, and then you do it again and again and again. In Python, you can do it functionally the same way. Same idea, slightly different syntax. You just don't bother saying what type of variable you want. Python will infer from the fact that there's a 0 right there. You don't need the parentheses. You do need the colon. You do need the indentation. You can't do the I++, but you can do this other technique, as we could have done in C as well. How else might we do this, though, too? Well, it turns out in C, we could do something like this, which, again, sort of cryptic at first glance, became perhaps more familiar, where you have an initialization, a conditional, and then an update that you do after each iteration. In Python, there isn't really an analog. There is no analog in Python where you have the parentheses and the multiple semicolons in the same line. Instead, there is a for loop, but it's meant to read a little more like English. For I in 0, 1, and 2. So we'll see in a bit, these square brackets represent an array, now to be called a list in Python. So lists in Python are more like linked lists than they are arrays. More on that soon. So this just means for I in the following list of 3 values. And on each iteration of this loop, Python automatically for you, it first sets I to 0, then it sets I to 1, then it sets I to 2, so that you effectively do things 3 times. But this doesn't necessarily scale, as I've drawn it on the board. Suppose you took this at face value as the way you iterate some number of times in Python using a for loop. At what point does this approach perhaps get bad or bad design? Let me give folks just a moment to think. Yeah, I'm back. Sure, if you don't know how many times you want to loop or iterate, you can't really create a hard-coded list like that of 0, 1, 2. Other thoughts? Yeah, if you're iterating a large number of times, this list is going to get longer and longer, and you're just kind of stupidly going to be typing out like comma 3, comma 4, comma 5, comma dot, 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 comma 99, comma 100. I mean, your code would start to look atrocious eventually. So there is a better way. In Python, there is a function, or technically a type, called range that essentially magically gives you back a range of values from 0 on up to, but not through a value. So the effect of this line of code, for I in the following range, essentially hands you back a list of 3 values, thereby letting you do something 3 times. And if you want to do something 99 times instead, you, of course, just change the 3 to a 99. Question?
Is there a way to start the beginning point of that range at a number or an integer that's higher than 0, or is there never really a point to do so?
A really good question. Can you start counting at a higher number? So not 0, which is the implied default, but something larger than that? Yes. So it turns out the range function takes multiple arguments, not just 1, but maybe 2 or even 3, that allows you to customize this behavior. So you can customize where it begins. You can customize the increment. By default, it's 1. But if you want to do every 2 values for like evens or odds, you could do that as well, and a few other things. And before long, we'll take a look at some Python documentation that will become your authoritative source for answers like that. Like, what can this function do? Other questions on this thus far? Seeing none. So what else might we compare and contrast here? Well, in the world of C, recall that we had a whole bunch of built-in data types like these here, bool and char and double and float and so forth, string, which happened to come from the CS50 library, but the language C itself certainly understood the idea of strings because the \0, the support for %s and printf, that's all native, built into C, not a CS50 simplification. All we did and revealed as of a couple of weeks ago is that string, this data type, is just a synonym for, a type def for char star, which is part of the language natively. In Python now, this list actually gets a little shorter, at least for these common primitive data types. Still going to have bools, we're going to have floats and ints, and we're going to have strings, but we're going to call them strs. And this is not a CS50 thing from the library. Str, str, is in fact a data type in Python that's going to do a lot more than strings did for us automatically in C. Ints and floats, meanwhile, don't need the corresponding longs and doubles, because in fact, among the problems Python solves for us too, ints can get as big as you want. Integer overflow is no longer going to be an issue per week 1. The language solves that for us. Floating point imprecision, unfortunately, is still a problem that remains. But there are libraries, code that other people have written, as we briefly discussed in weeks past, that allow you to do scientific or financial computing using libraries that build on top of these data types as well. So there's other data types too in Python, which we'll see actually gives us a whole bunch of more power and capability. Things called ranges, like we just saw. Lists, like I called out verbally with the square brackets. Things called tuples for things like x comma y or latitude comma longitude. Dictionaries or dicts, which allow you to store keys and values, much like our hash tables from last time. And then sets in the mathematical sense, where they filter out duplicates for you. And you can just put a whole bunch of numbers, a whole bunch of words or whatnot. And the language, via this data type, will filter out duplicates for you. Now, there's going to be a few functions we give you this week and beyond, training wheels that we're then going to very quickly take off, just because, as we'll see today, they just simplify the process of getting user input correctly without accidentally writing buggy code just when you're trying to get hello world or something similar to work. And we'll give you functions not as long as this list in C, but a subset of these. Get float, get int, and get string. That'll automate the process of getting user input in a way that's more resilient against potential bugs, but we'll see what those bugs might be. And the way we're going to do this is similar in spirit to C. Instead of doing include CS50.h, like we did in C, you're going to now start saying import CS50. Python supports, similar to C, libraries, but there aren't header files anymore. You just use the name of the library in Python. And if you want to import CS50's functions, you just say import CS50. Or if you want to be more precise and not just import the whole thing, which could be slow if you've got a really big library with a lot of functionality in it, you can be more precise and say from CS50 import get float. From CS50 import get int. From CS50 import get string. Or you can just separate them by commas and import 3 and only 3 things from a particular library like ours. But starting today and onward, we're going to start making much more heavy use of libraries, code that other people wrote, so that we're no longer reinventing the wheel. We're not making our own linked lists, our own trees, our own dictionaries. We're going to start standing on the shoulders of others so that you can get real work done, so to speak, faster by building your software on top of others' code as well. All right, so that's it for the syntactic tour of the language and the sort of core features. Soon we'll transition to application thereof. But let me pause here to see if there's any questions on syntax or primitives or otherwise. Or otherwise. No? Oh, yes, and back. Sorry, say it again. Why doesn't Python have what kind of operators? Sorry, someone coughed when you said something operators. The increment operator? I'd have to check the history, honestly. Python has tended to be a fairly minimalist language. And if you can do something one way, the community arguably has tended to not give you multiple ways to do the same thing syntactically. There's probably a better answer. And I'll see if I can dig in and post something online to follow up on that. All right, so before we transition to now writing some actual code, let me go ahead and consider exactly how we're going to write code. In the world of C, recall that it's generally been a 2-step process. We create a file called like hello.c, and then step 1, make hello. Step 2, /hello. Or if you think back to week 2, when we sort of peeled back the layer of what what make was doing, you could more verbosely type out the name of the actual compiler, Clang in our case, command line arguments like -o hello to specify what name you want to create. And then you can specify the file name. And then you can specify what libraries you want to link in. So that was a very verbose approach, but it was always a 2-step approach. And so even as you've been doing recent problem sets, odds are you've realized that anytime you want to make a change to your code or make a change to your code and try and test your code again, you're constantly doing those 2 steps. Moving forward in Python, it's going to become simpler, and it's going to be just this. The file name is going to change, but that might go without saying. It's going to be something like hello.py, py, instead of hello.c. And that's just a convention using a different file extension. But there's no compilation step per se. You jump right to the execution of your code. And so Python, it turns out, is the name not only of the language we're going to start using, it's also the name of a program on a Mac, a PC, assuming it's been pre-installed, that interprets the language for you. This is to say that Python is generally described as being interpreted, not compiled. And by that, I mean you get to skip, from the programmer's perspective, that compilation step. There is no manual step in the world of Python, typically, of writing your code and then compiling it to zeros and ones and then running the zeros and ones. Instead, these kind of two steps get collapsed into the illusion of one, whereby you instead are able to just run the code and let the computer figure out how to actually convert it to something the computer understands. And the way we do that is via this old process, input and output. But now, when you have source code, it's going to be passed into an interpreter, not a compiler. And the best analog of this is just to perhaps point out that in the human world, if you speak or don't speak multiple human languages, it can be a pretty slow process from going from one language to another. For instance, here are step-by-step instructions for finding someone in a phone book, unfortunately in Spanish. Unfortunately, if you don't speak or read Spanish, you could figure this out. You could run this algorithm, but you're going to have to do some Googling, or you're going to have to open up literal dictionary from Spanish to English and convert this. And the catch with translating any language, human or computer or otherwise, is that you're going to pay a price, typically some time. And so converting this in Spanish to this in English is just going to take you longer than if this were already in your native language. And that's going to be one of the subtleties with the world of Python. Yes, it's a feature that you can just run the code without having to bother compiling it manually first. But we might pay a price, and things might be a little slower. Now, there's ways to chip away at that, but we'll see an example thereof. In fact, let me transition now to just a couple of examples that demonstrate how Python is not only easier for many people to use, perhaps yourselves too, because it throws away a lot of the annoying syntax. It shortens the number of lines you have to write. And also, it comes with so many darn libraries. You can just do so much more without having to write the code yourself. So as an example of this, let me switch over here to this image from problem set 4, which is the Weeks Bridge down by the Charles River here in Cambridge. And this is the original photo. Pretty clear, and it's even higher res if we looked at the original version of the photo. But there have been no filters a la Instagram applied to this photo. Recall for problem set 4, you had to implement a few filters, and among them might have been blur. And blur was probably among the more challenging of the ones, because you had to iterate over all of the pixels. You had to take into account what's above, what's below, to the left, to the right. I mean, there was a lot of math and arithmetic. And if you ultimately got it, it was probably a great sense of satisfaction. But that was probably several hours later. In a language like Python, where there might be libraries that have been written by others on whose shoulders you can stand, we could perhaps do something like this. Let me go ahead and run a program, or write a program called blur.py here. And in blur.py, in VS Code, let me just do this. Let me import from a library, not the CS50 library, but the pillow library, so to speak, a keyword called image and another one called image filter. Then let me go ahead and say, let me open the current version of this image, which is called bridge.bmp. So the before version of the image will be the result of calling image.open, quote unquote, bridge.bmp. And then let me create an after version. So you'll see before and after. After equals the before version dot filter of image filter. And there is, if I read the documentation, I'll see that there's something called a box blur that allows you to blur in box format, like one pixel above, below, left, and right. So I'll do one pixel there. And then after that's done, let me go ahead and save the file as something like out.bmp. That's it. Assuming this library works as described, I am opening the file in Python using line 3. And this is somewhat new syntax. In the world of Python, we're going to start making use of the dot operator more. Because in the world of Python, you have what's called object-oriented programming, or OOP as a term of art. And what this means is that you still have functions, you still have variables, but sometimes those functions are embedded inside of the variables, or more specifically, inside of the data types themselves. Think back to C. When you wanted to convert something to uppercase, there was a toUpper function that takes as input an argument that's a char. And you can pass in any char you want, and it will uppercase it for you and give you back a value. Well, you know what? If that's such a common paradigm where uppercasing chars is a useful thing, what the world of Python does is it embeds into the string data type, or char if you will, the ability just to uppercase any char by treating the char or the string as though it's a struct in C. Recall that structs encapsulate multiple types of values. In object-oriented programming, in a language like Python, you can encapsulate not just values, but also functionality. Functions can now be inside of structs. But we're not going to call them structs anymore. We're going to call them objects. But that's just a different vernacular. So what am I doing here? Inside of the image library, there's a function called open. And it takes an argument, the name of the file, to open. Once I have a variable called before, that is a struct, or technically an object, inside of which is now, because it was returned from this function, a function called filter that takes an argument. The argument here happens to be image.boxblur1, which itself is a function, but it just returns the filter to use. And then after.save does what you might think. It just saves the file. So instead of using fopen and fwrite, you just say .save. And that does all of that messy work for you. So it's just, what, 4 lines of code total? Let me go ahead and go down to my terminal window. Let me go ahead and show you with ls that at the moment, whoops, sorry, let me not bother showing that because I have other examples to come. I'm going to go ahead and do Python of blur.py. Nope, sorry, wrong place. I did need to make a command. There we go. OK, let me go ahead and type ls inside of my filter directory, which is among the sample code online today. There's only one file called bridge.b. Damn it. I'm trying to get these things ready at the same time. Let me rewind. Let me move this code into place. All right, I've gone ahead and moved this file, blur.py, into a folder called filter, inside of which there's another file called bridge.bmp, which we can confer with ls. Let me now go ahead and run Python, which is my interpreter and also the name of the language, and run Python on this file. So much like running the Spanish algorithm through Google Translate or something like that as input to get back the English output, this is going to translate the Python language to something this computer or this cloud-based environment understands, and then run the corresponding code top to bottom, left to right. I'm going to go ahead and enter. No error message is generally a good thing. If I type ls, you'll now see out.bmp. Let me go ahead and open that. And you know what? Just to make clear what's really happening, let me blur it even further. Let's make a box that's not just 1 pixel around, but 10. So let's make that change. And let me just go ahead and rerun it with Python of blur.py. I still have out.bmp. Let me go ahead and open out.bmp and show you first the before, which looks like this. That's the original. And now, crossing my fingers, 4 lines of code later, the result of blurring it as well. So the library is doing all of the same kind of legwork that you all did for the assignment, but it's encapsulated it all into a single library that you can then use instead. Those of you who might have been feeling more comfortable might have done a little something like this. Let me go ahead and open up one other file called edges.py. And in edges.py, I'm again going to import from the pillow library the image keyword and the image filter. Then I'm going to go ahead and create a before image that's a result of calling image.open of the same thing, bridge.bmp. Then I'm going to go ahead and run a filter on that called image filter.findEdges, which is like a constant, if you will, defined inside of this library for us. And then I'm going to do after.save, quote unquote, out.bmp, using the same file name. I'm now going to run Python of edges.py. After, sorry, user error. We'll see what syntax error means soon. Let me go ahead and run the code now, edges.py. Let me now open that new file, out.pmp. And before we had this. And now, especially what will look familiar if you did the more comfortable version of pset4, we now get this after just 4 lines of code. So again, suggesting the power of using a language that's better optimized for the tool at hand. And at the risk of really making folks sad, let's go ahead and re-implement, if we could, problem set 5 real quickly here. Let me go ahead and open another version of this code wherein I have a C version just from problem set 5, wherein you implemented a spell checker, loading 100,000 plus words into memory. And then you kept track of just how much time and memory it took. And that probably took a while, implementing all of those functions in dictionary.c. Let me instead now go into a new file called dictionary.py. And let me stipulate for the sake of discussion that we already wrote in advance speller.py, which corresponds to speller.c. You didn't write either of those. Recall for problem set 5, we gave you speller.c. Assume that we're going to give you speller.py. So the onus on us right now is only to implement dictionary.py. All right, so I'm going to go ahead and define a few functions. And we're going to see now the syntax for defining functions in Python. I want to go ahead and define first a hash table, which was the very first thing you defined in dictionary.c. I'm going to go ahead then and say words gets this. Give me a dictionary, otherwise known as a hash table. All right, now let me define a function called check, which was the first function you might have implemented. Check is going to take a word. And you'll see in Python, the syntax is a little different. You don't specify the return type. You use the word def instead to define. You still specify the name of the function and any arguments there too, but you omit any mention of types. But you do use a colon and indent. So how do I check if a word is in my dictionary or in my hash table? Well, in Python, I can just say if word in words, go ahead and return true. Else, go ahead and return false. Done with the check function. All right, now I want to do like load. That was the heavy lift where you had to load the big file into memory. So let me define a function called load. It takes a string, the name of a file, to load. So I'll call that dictionary, just like in C, but no data type. Let me go ahead and open a file by using an open function in Python by opening that dictionary in read mode. So this is a little similar to fopen, a function in C you might recall. Then let me iterate over every line in the file. In Python, this is pretty pleasant. For line in file, colon, indent. How now do I get at the current word and then strip off the new line? Because in this file of words, the 140,000 words, there's word /n, word /n. All right? Well, let me go ahead and get a word from the current line, but strip off from the right end of the string the new line, which the rstrip function in Python does for me. Then let me go ahead and add to my dictionary or hash table that word. Done. Let me go ahead and close the file for good measure. And then let me go ahead and return true because all was well. That's it for the load function in Python. How about the size function? This did not take any arguments. It just returns the size of the hash table or dictionary. In Python, I can do that by returning the length of the dictionary in question. And then lastly, gone from the world of Python is malloc and free. Memory is managed for you. So no matter what I do, there's nothing to unload. The computer will do that for me. So I give you in these functions problem set 5 in Python. So I'm sorry, we made you write it in C first. But the implication now is that what are you getting for free in a language like Python? Well, encapsulated in this one line of code is much of what you wrote for problem set 5, implementing your array for all of your letters of the alphabet or more, all of the linked lists that you implemented to create chains to store all of those words. All of that is happening. It's just someone else in the world wrote that code for you, and you can now use it by way of a dictionary. And actually, I can change this a little bit because add is technically not the right function to use here. I'm actually treating the dictionary as something simpler, a set. So I'm going to make one tweak. Set, recall, was another data type in Python. But set just allows it to handle duplicates, and it allows me to just throw things into it by literally using a function as simple as add. And I'm going to make one other tweak here. Because when I'm checking a word, it's possible it might be given to me in uppercase or capitalized. It's not going to necessarily come in the same lowercase format that my dictionary did. I can force every word to lowercase by using word.lower. And I don't have to do it character for character. I can do the whole darn string at once by just saying word.lower. All right, let me go ahead and open up a terminal window here. And let me go into first my C version on the left. And actually, I'm going to go ahead and split my terminal window into two. And on the right, I'm going to go into a version that I essentially just wrote, but it's also available online if you want to play along afterward. I'm going to go ahead and make speller in C on the left. And note that it takes a moment to compile. Then I'm going to be ready to run speller of dictionaries. Let's do like the Sherlock Holmes text, which is pretty big. And then over here, let me get ready to run Python of speller on texts/holmes.txt2. So the syntax is a little different at the command prompt. I just, on the left, have to compile the code with make and then run it with /speller. On the right, I don't need to compile it, but I do need to use the interpreter. So even though the lines are wrapping a little bit here, let me go ahead and run it on the right. And I'm going to count how long it takes verbally for demonstration's sake. 1 Mississippi, 2 Mississippi, 3 Mississippi. OK, so it's like 3 seconds, give or take. Now running it in Python, keeping in mind, I spent way fewer hours implementing a spell checker in Python than you might have in problem set 5. But what's the trade-off going to be? And what kinds of design decisions do we all now need to be making consciously? Here we go, on the right in Python. 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi, 6 Mississippi, 7 Mississippi, 8 Mississippi, 9 Mississippi, 10 Mississippi, 11 Mississippi. All right, so 10 or 11 seconds. So which one is better? Let's go to the group here. Which of these programs is the better one? How might you answer that question based on demonstration alone? What do you think?
I think Python is better for the programmer, or more comfortable for the programmer, but C is better for the user.
OK, so Python, to summarize, is better for the programmer because it was way faster to write. But C is maybe better for the computer because it's much faster to run. I think that's a reasonable formulation. Other opinions? Yeah.
I think it depends on the size of the project that you're dealing with. So if it's going to be something that's relatively quick, I might not care that it takes 10 seconds to do it, and it took me way faster to do it in Python. Whereas in C, if I'm dealing with something like a massive data set or something huge that that time is going to really build up on, it might be worth it to put in the upfront effort and just coding it in C so that the process continually runs faster over a longer period of time.
Absolutely. A really good answer. And let me summarize is it depends on the workload, if you will. If you have a very large data set, you might want to optimize your code to be as fast and performant as it can be, especially if you're running that code again and again. Maybe you're a company like Google. People are searching a huge database all the time. You really want to squeeze every bit of performance as you can out of the computer. You might want to have someone smart take a language like C and write it at a very low level. It's going to be painful. They're going to have bugs. They're going to have to deal with memory management and but if and when it works correctly, it's going to be much faster, it would seem. By contrast, if you have a data set that's big, and 140,000 words is not small, but you don't want to spend 5 hours, 10 hours, a week of your time building a spell checker or a dictionary, you can instead leverage a different language with different libraries and build on top of it in order to prioritize the human time instead. Other thoughts? That perfect segue to exactly the next point we wanted to make, which was, is there something in between? And indeed, there is. I'm oversimplifying what this language is actually doing. It's not as stark a difference as saying, hey, Python is 4 times slower than C. That's not the right takeaway. There are absolutely ways that engineers can optimize languages as they have already done for Python. And in fact, I've configured my settings in such a way that I've kind of dramatized just how big the difference is. It is going to be slower Python typically than the equivalent C program, but it doesn't have to be as big of a gap as it is here, because indeed, among the features you can turn on in Python is to save some intermediate results. Technically speaking, yes, Python is interpreting dictionary.py and these other files, translating them from one language to another. But that doesn't mean it has to do that every darn time you run the program. As you propose, you can save or cache, C-A-C-H-E, the results of that process so that the second time and the third time are actually notably faster. And in fact, Python itself, the interpreter, the most popular version thereof, itself is actually implemented in C. So you can make sure that your interpreter is as fast as possible. And what then is maybe the high-level takeaway? Yes, if you are going to try to squeeze every bit of performance out of your code, and maybe code is constrained. Maybe you have very small devices. Maybe it's like a watch nowadays. Or maybe it's a sensor that's installed in some small format in an appliance or in infrastructure where you don't have much battery life and you don't have much size. You might want to minimize just how much work is being done. And so the faster the code runs, and the better it's going to be if it's implemented something low level. So C is still very commonly used for certain types of applications. But again, if you just want to solve real world problems and get real work done, and your time is just as, if not more valuable than the device you're running it on long term, you know what? Python is among the most popular languages as well. And frankly, if I were implementing a spell checker moving forward, I'm probably starting with Python. And I'm not going to waste time implementing all of that low-level stuff, because the whole point of using newer, modern languages is to use abstractions that other people have created for you. And by abstraction, I mean something like the dictionary function that just gives you a dictionary or a hash table, or the equivalent version that I used, which in this case was a set. All right, any questions then on Python thus far? No? All right, oh yeah, in the middle. Really good question or observation. Could you just compile Python code? Yes, absolutely. This idea of compiling code or interpreting code is not native to the language itself. It tends to be native to the conventions that we humans use. So you could actually write an interpreter for C that would read it top to bottom, left to right, converting it to, on the fly, something the computer understands. But historically, that's not been the case. C is generally a compiled language, but it doesn't have to be. What Python nowadays is actually doing is what you described earlier. It technically is, sort of unbeknownst to us, compiling the code, technically not into zeros and ones, technically into something called bytecode, which is this intermediate step that just doesn't take as much time as it would to recompile the whole thing. And this is an area of research for computer scientists working in programming languages to improve these kinds of paradigms. Why? Well, honestly, for you and I, the programmer, it's just much easier to, one, run the code and not worry about the stupid second step of compiling it all the time. Why? It's literally half as many steps for me, the human, and that's a nice thing to optimize for. And ultimately, two, you might want all of the fancy features that come with these other languages. So you should really just be fine-tuning how you can enable these features as opposed to shying away from them here. And in fact, the only time I personally ever use C is from like September to October of every year during CS50. Almost every other month do I reach for Python or another language called JavaScript to actually get real work done, which is not to impugn C. It's just that those other languages tend to be better fits for the amount of time I have to allocate and the types of problems that I want to solve. All right, let's go ahead and take a 5-minute break here. And when we come back, we'll start writing some programs from scratch. All right, so let's go ahead and start writing some code from the beginning here, whereby we start small with some simple examples, and then we'll build our way up to more sophisticated examples in Python. But what we'll do along the way is first look side by side at what the C code looked like way back in week 1 or 2 or 3 and so forth, and then write the corresponding Python code at right, and then we'll transition just to focusing on Python itself. What I've done in advance today is I've downloaded some of the code from the course's website, my source 6 directory, which contains all of the pre-written C code from weeks past, but it'll also have copies of the Python code we'll write here together and look at. So first, here is hello.c back from week 0. This was version 0 of it. I'm going to go ahead and do this. I'm going to go ahead and split my code window up here. I'm going to go ahead and create a new file called hello.py. And this isn't something you'll typically have to do, laying your code out side by side. But I've just clicked the little icon in VS Code that looks like 2 columns that splits my code editor into 2 places so that we can, in fact, see things for now side by side with my terminal window down below. All right, now I'm going to go ahead and write the corresponding Python program on the right, which, recall, was just print, quote unquote, hello world, and that's it. Now down in my terminal window, I'm going to go ahead and run Python of hello.py, enter, and voila, we've got hello.py working. So again, I'm not going to play any further with the C code. It's there just to jog your memory left and right. So let's now look at a second version of hello world from that first week, whereby if I go and get hello1.c, I'm going to drag that over to the right. Whoops. I'm going to go ahead and drag that over to the left here. And now on the right, let's modify hello.py to look a little more like this second version in C. All right, I want to get a answer from the user as a return value, but I also want to get some input from them. So from CS50, I'm going to import the function called getString for now. We're going to get rid of that eventually, but for now it's a helpful training wheel. And then down here, I'm going to say answer equals getString, quote unquote, what's your name, question mark, space, but no semicolon, no data type. And then I'm going to go ahead and print, just like the first example on the slide, hello, comma, space, plus answer. And now let me go ahead and run this. Python of hello.py. All right, it's asking me what's my name, David, hello, comma, David. But it's worth calling attention to the fact that I've also simplified further. It's not just that the individual functions are simpler. What is also now glaringly omitted from my Python code at right, both in this version and the previous version? What did I not bother implementing? Yeah, so I didn't even need to implement main. We'll revisit the main function because having a main function actually does solve problems sometimes, but it's no longer required. In C, you have to have that to kickstart the entire process of actually running your code. And in fact, if you were missing main, as you might have experienced if you accidentally compiled helpers.c instead of the file that contained main, you would have seen a compiler error. In Python, it's not necessary. Python, you can just jump right in, start programming, and boom, you're good to go. Especially if it's a small program like this, you don't need the added overhead or complexity of a main function. So that's one other difference here. All right, there were a few other ways we could say hello world. Recall that I could use a format string. So I could put this whole thing in quotes. I could use this f prefix. And then let me go ahead and run Python of hello.py again. You can perhaps see where we're going with this. Let me type my name, David, and here we go. OK, that's the mistake that someone identified earlier. You need the curly braces. Otherwise, no variables are interpolated, that is, substituted with their actual values. So if I go back in and add those curly braces to the f string, now let me run Python of hello.py, type in my name, and there we go. We're back in business. Which one's better? I mean, it depends. But generally speaking, making shorter, more concise code tends to be a good thing. So stylistically, the f string is probably a reasonable instinct to have. All right, well, what more can we do besides this? Well, let me go ahead here and let's get rid of the training wheel altogether, actually. So same C code at left. Let me get rid of the CS50 library, which we will ultimately in a couple of weeks anyway. I can't use getString, but I can use a function that comes with Python called input. And in fact, this is actually a one-for-one substitution pretty much. There's really no downside to using input instead of getString. We implement getString just for consistency with what you saw in C. Python of hello.py, what's your name, David, still actually works the same. So gone are the CS50 specific training wheels, but we're going to bring them back shortly just to deal with integers or floats or other values too, because it's going to make our lives a little simpler with error checking. All right, any questions before we now pivot to revisiting other examples from week 1, but now in Python? All right, let me go ahead and open up now, let's say calculator0.c, which was one of the first examples we did involving math and operators like that, as well as functions like getInt. Let me go ahead and create a new file now called calculator.py. at right, so that I have my C code at left still and my Python code at right. All right, let me go dive into a translation of this code into Python. I am going to use getInt from the CS50 library, so let me import that. I'm going to go ahead now and get an int from the user. So x equals getInt, and I'll ask them for an x value, just like we did weeks ago. No need to specify a semicolon, though, or a int for the x. It will just figure it out. Y is going to get another int via y colon. And then down here, I'm going to go ahead and say print of x plus y. So this is already a bit new. Recall the C version required that I use this format string as well as printf itself. Python's just a little more user-friendly. If all you want to do is print out a value like x plus y, just print it. Don't futz with any percent signs or format codes. It's not printf. It's indeed just print now. All right, let me go ahead and run Python of calculator.py. Enter. And just do a quick sample. 1 plus 2 indeed equals 3. As an aside, suppose I had taken a different approach to importing the whole CS50 library. Functionally, it's the same. You're not going to notice any performance impact here. It's a small library. But notice what does not work now, whereas it did work in C. Python of calculator.py, enter. We see our first traceback deliberately here. So a traceback is just a term of art that says here is a trace back through all of the functions that just got executed. In the world of C, you might call this a stack trace. Stack being the operative word. Recall that when we talked about the stack and the heap, the stack, like a stack of trays, was all of the functions that might get called one after the other. We had main, we had swap, then swap went away, and then main finished. Recall. So here's a traceback of all of the functions or code that got executed. There's not really any functions other than my file itself. Otherwise, there'd be more detail. But even though it's a little cryptic, we can perhaps infer from the output here. Name error. So something related to the name of something. Name getInt is not defined. And this, of course, happens on line 3 over there. All right, so why is that? Well, Python essentially allows us to namespace our functions that come from libraries. There was a problem in C. If you were using the CS50 library and thus had access to getInt, getString, and so forth, you could not use another library that had the same function names. They would collide, and the compiler would not know how to link them together correctly. In Python and other languages like JavaScript and in Java, you have support for effectively what would be called namespaces. You can isolate variables and function names to like their own namespace, like their own container in memory. And what this means is if you import all of CS50, you have to say that the getInt you want is inside the CS50 library. So just like with the image blurring and the image edges before, where I had to specify image dot and image filter dot, similarly here, am I specifying with a dot operator, albeit a little differently, that I want CS50.getInt in both places. And now if I rerun Python of calculator.py, 1 and 2, now we're back in business. Which one is better? Generally speaking, it depends on just how many functions you're using from the library. If you're using a whole bunch of functions, just import the whole thing. If you're only using maybe 1 or 2, import them line by line. All right, so let's go ahead and make a little tweak here. Let's get rid of this library and take this training wheel off too, as quickly as we introduced it. Though for the problem set 6, you'll be able to use all of these same functions. Suppose I get rid of this and I just use the input function, just like I did by replacing getString earlier. Let me go ahead now and run this version of the code, Python of calculator.py. OK, how about 1 plus 2 equals 3? Huh. All right, obviously wrong, incorrect. Can anyone explain what just happened based on instincts? What just happened here? Yeah. Sure, yeah. Exactly. Python is interpreting both, or treating both x and y as strings, which is actually what the input function returns by default. And so plus is now being interpreted as concatenation as we defined it earlier. So x plus y isn't x plus y mathematically, but in terms of string joining, just like in Scratch. So that's why we're getting 12, or really 1, 2, which isn't itself a number. It too is another string. So we somehow need to convert things. And we didn't have this ability quite as easily in C. We did have like the a to I function, ASCII to integer, which did allow you to do this. The analog in Python is actually just to do a cast, a typecast using int. So just like in C, you can use the keyword int, but use it a little differently. Notice that I'm not doing parenthesis, int, close parenthesis before the value. I'm using int as a function. So indeed, in Python, int is a function, float is a function that you can pass values into to do this kind of conversion. So now if I run python of calculator.py, 1 and 2, now we're back in business and getting the answer of 3. But there's kind of a catch here. There's always going to be a trade-off. Like, that sounds amazing that it just works in this way. We can throw away the CS50 library already. But what if the user accidentally types or maliciously types in, like, a cat instead of a number? Damn, well, there's one of these tracebacks. Like, now my program has crashed. This is similar in spirit to the kinds of seg faults that you might have had in C. But they're not seg faults per se. It doesn't necessarily relate to memory. This time it relates to actual runtime values not being as expected. So this time it's not a name error. It's a value error. Invalid literal for int with base 10, quote unquote, cat. So again, it's written for sort of a programmer more than sort of a typical person, because it's pretty arcane, the language here. But let's try to interpret it. Invalid literal. A literal is just something someone typed for int, which is the function name, with base 10. It's defaulting to decimal numbers. CAT is apparently not a decimal number. It doesn't look like it, therefore can't be treated like it. Therefore, there's a value error. So what can we do? Unfortunately, you would have to somehow catch this error. And the only way to do that in Python really is by way of another feature that C did not have, namely what are called exceptions. An exception is exactly what just happened. Name error, value error. They are things that can go wrong when your Python code is running that aren't necessarily going to be detected until you run your code. So in Python and in JavaScript and in Java and other more modern languages, there's this ability to actually try to do something except if something goes wrong. And in fact, I'm going to introduce a bit of syntax here, even though we won't have to use this much just yet. Instead of just blindly converting x to an int, let me go ahead and try to do that. And if there's an exception, go ahead and say something like print that is not an int. And then I'm going to do something like exit right there. And let me go ahead and do this here. Let me try to get y, except if there's an exception. Then let me go ahead and say, again, that is not an int, exclamation point. And then I'm going to exit from there too. Otherwise, I'll go ahead and print x plus y. If I run python of calculator.py now, whoops. Oh, forgot my close quote. Sorry. All right, so close quote. Python of calculator.py, 1 and 2 still work. But if I try to type in something wrong like cat, now it actually detects the error. So what is the CS50 library in Python doing? It's actually doing that try and except for you. Because suffice it to say, otherwise your programs for something simple like a calculator start to get longer and longer. So we factored that kind of logic out to the CS50 getInt function and getFloat function. But underneath the hood, they're essentially doing this. Try, except, but they're being a little more precise. They're detecting a specific error, and they are doing it in a loop so that these functions will get executed again and again. In fact, the best way to do this is to say, except if there's a value error, then print that error message out to the user. And again, let's not get too into the weeds here with this feature. We've already put it into the CS50 library, but that's why, for instance, we bootstrap things by just using these functions out of the box. All right, let's do something more with our calculator here. How about this? In the world of C, we had another version of this code which actually did some division by way of, which actually did division of numbers, not just the addition herein. So let me go ahead and close the C version. And let's focus only on Python now, doing some of these same lines of codes. But I'm going to go ahead and just assume that the user is going to cooperate and use proper input. So from CS50, import getInt. That'll deal with any errors for me. X gets getInt, ask the user for an int x. Y equals getInt, ask the user for an int y. And then let's go ahead and do this. Let's declare a variable called z, set it equal to x divided by y. Then let's go ahead and print z. Still no need for a format string. I can just print out the variable's value. Let me go ahead and run python of calculator.py. Let me do 1, 10, and I get 0.1. What did I get in C, though? If you think back, what would we have happened in C? Yeah, we would have gotten 0 in C, but why in C? When you divide one int by another, and those ints are like 1 and 10, respectively. It will give you what? It will give you an integer back, and unfortunately, 0.1, the integer part of it is indeed 0. So this was an example of truncation. So truncation was an issue in C, but it would seem as though this is no longer a problem in Python insofar as the division operator actually handles that for us. As an aside, if you want the old behavior, because it actually is sometimes useful for rounding or flooring values, you can actually use 2 slashes, and now you get the C behavior, so that now 1 divided by 10 is 0. So you don't give up that capability, but at least it does a more sensible default. Most people, especially new programmers, when dividing one value by another, would want to get 0.1, not 0, for reasons that indeed we had to explain weeks ago. But what about another problem we had with the world of floats before, whereby there is imprecision? Let me go ahead and somewhat cryptically print out the value of z as follows. I'm going to format it using an f string, and I'm going to go ahead and format not just z, because this is essentially the same thing. Notice this. If I do Python of calculator.py, 1 and 10, I get by default just one significant digit. But if I use this syntax in Python, which we won't have to use often, I can actually do in C, like I did before, 50 significant digits after the decimal point. So now let me rerun Python of calculator.py, 1 and 10. And let's see if floating point imprecision is still with us. Unfortunately, it is. And you can see as much here. The f string, the format string, is just showing us now 50 digits instead of the default 1. So we've not solved all problems, but we have solved at least some. All right, before we pivot away from a mere calculator, any questions now on syntax or concepts or the like? Yeah?
So you use like this double slash to get the answer. How do you comment?
How do you what? Oh, how do you comment? Really good question. If you're using double slash for division with flooring or truncation, like I described, how do you do a comment in Python? This is a comment. And the convention is actually to use a complete sentence, like with a capital T here. You don't need a period unless there's multiple sentences. And technically, it should be above the line of code by convention. So you would use a hash symbol instead. Good question. Haven't seen those yet. All right, let's go ahead and make something else here. How about? Let me go ahead and open up, for instance, an example called points1.c, which we saw a few weeks back. And let me go ahead on the other side and create a file called points.py. This was a program, recall, that asked the user how many points they lost on the first assignment. And then it went ahead and just printed out whether they lost fewer points than me, because I lost 2 if you recall the photo, more points than me, or the same points as me. Let me go ahead and zoom out so we can see a bit more of this. And let me now, on the top right here, go about implementing this in Python. So I want to first prompt the user for some number of points. So from CS50, let's import getInt, so it handles the error checking. Let's then do points equals getInt and ask the user, how many points did you lose? Question mark. Then let's go ahead and say if points less than 2, which was my value, print you lost fewer points than me. Otherwise, if it's else if points greater than 2, go ahead and print you lost more points than me. Else, let's go ahead and handle the final scenario, which is you lost the same number of points as me. Before I run this, does anyone want to point out a mistake I've already made? Yeah. Yeah, so else if in C is actually now elif in Python. It's a single word. So let me change this to elif. And now cross my fingers. Python of points.py. Suppose you lost 3 points on some assignment. You lost more points than my 2. If you only lost 1 point, you lost fewer points than me. So the logic is the same. But notice the code is much tighter. In 10 total lines, we did in what was 24 lines, because we've thrown away a lot of the syntax. The curly braces are no longer necessary. The parentheses are gone. The semicolons. So this is why it just tends to be more pleasant pretty quickly using a language like this. All right, let's do one other example here. In C, recall that we were able to determine the parity of some number, if something is even or odd. Well, in Python, let me go ahead and create a file called parity.py. And let's look for a moment at the C version at left. Here was the code in C that we used to determine the parity of a number. And really, the key takeaway from all these lines was just the remainder operator. And that one is still with us. So this is a simple demonstration just to make that point. If in Python I want to determine whether a number is even or odd, well, let's go ahead and from CS50 import getInt. Then let's go ahead and get a number like n from the user using getInt and ask them for n. And then let's go ahead and say if n %2 equals 0, then let's go ahead and print quote unquote even. Else, let's go ahead and print out odd. But before I run this, anyone want to instinctively, even though we've not talked about this, point out a mistake here? What I do wrong? Yeah, so double equals. Again, so even though some of the stuff is changing, some of the same ideas are the same. So this too should be a double equal sign because I'm comparing for equality here. And why is this the right math? Well, if you divide a number by 2, it's either going to have 0 or 1 as a remainder. And that's going to determine if it's even or odd for us. So let's run Python of parity.py, type in a number like 50, and hopefully we get indeed even. So again, same idea, but now we're down to 8 lines of code instead of the 20. Well, let's now do something a little more interactive and a little representative of tools that actually ask the user questions. In C, recall that we had this agreement program, agree.c. And then let's go ahead and implement a corresponding version in Python in a file called agree.py. And let's look at the C version first. On the left, we used getChar here. And then we use the double vertical bars to check if C is equal to capital Y or lowercase y. And then we did the same thing for n for no. And so let's go over here. And let's do from CS50 import get. OK, getChar is not a thing. And this here is another difference with Python. There is no data type for individual characters. You have strings, strs, and honestly, those are fine. Because if you have a str that's just one character, for all intents and purposes, it is just a single character. So it's just a simplification. You don't have to think as much. You don't have to worry about double quotes, single quotes. In fact, in Python, you can use double quotes or single quotes so long as you're consistent. So long as you're consistent, the single quotes do not mean something different like they do in C. So I'm going to go ahead and use getString here. Although strictly speaking, I could just use the input function, as we saw before. I'm going to get a string from the user that asks them this. GetString, quote unquote, do you agree? Like a little checkbox or interactive prompt where you have to say yes or no, you want to agree to the following terms or whatnot. And then let's translate the conditionals to Python now too. So if s equals quote unquote y, or s equals lowercase y, let's go ahead and print out agreed, just like in C. If s equals n, or s equals little n, let's go ahead then and print out not agreed. And you can already see perhaps one of the differences here too is Python a little more English-like in that you just literally use the English word or instead of the 2 vertical bars, but it's ultimately doing the same thing. Can we simplify this code a bit, though? This would be a little annoying if we wanted to add support, not just for big Y and little y, but yes, or big yes, or little yes, or big Y, lowercase e, capital S, right? There's a lot of permutations of YES, or just Y, that we ideally should tolerate. Otherwise, the user is going to have to type exactly what we want, which isn't very user-friendly. Any intuition for how we could logically, even if you don't know how to do it in code, make this better? Yeah. Nice. Yeah, we saw an example of a list before, just 0, 1, 2. Why don't we take that same idea and ask a similar question? If s is in the following list of values, y, or little y, or heck, let me add to the list now, yes, or maybe all capital yes. And it's going to get a little annoying, admittedly, but this is still better than the alternative with all the ors. I could do things like this and so forth. There's a whole bunch more permutations, but let's leave this alone. And let me just go into here and change this too. If s is in the following list of n, or little n, or no, and I won't do as, let's just not worry about the weird capitalizations there for now. Let's go ahead and run this. Python of agree.py. Do I agree? Y. OK, how about yes? All right, how about big yes? OK, that does not seem to work. Notice it did not say agreed, and it did not say not agreed. It didn't detect it. So how can I do this? Well, you know what I could do? I don't really need the uppercase and lowercase. Let me tighten this list up a little bit. And why don't I just force s to be lowercase? S.lower, recall, whether it's one character or more, is a function built into strs now, strings in Python, that forces the whole thing to lowercase. So now watch what I can do. Python of agree.py, little y, that works. Big Y, that works. Big yes, that works. Big Y, little e, big S, that also works. So we've now handled in one fell swoop a whole bunch more logic. And you know what? We can tighten this up a bit. Here's an opportunity in Python for slightly better design. What have I done in here that's a little redundant? Does anyone see an opportunity to eliminate a redundancy? Doing something more than times than you need is a stretch or no? Yep. We could move the s.lower above. Notice that I'm using s.lower twice, but it's going to give me the same answer both times. So I could do a couple of things here. I could, first of all, get rid of this lower and get rid of this lower. And then above this, maybe I could do something like this. S equal, I can't just do this because that throws the value away. It does the math, but it doesn't convert the string itself. It's going to return a value. So I have to say s equals s.lower. I could do that. Or honestly, I can chain these things together. And this is not something we saw in C. If getString returns a string, and strings have functions like lower in them, you can chain these functions together like this and do dot this, dot that, dot this other thing. And eventually you want to stop because it's going to become crazy long. But this is reasonable. Still fits on the screen. It's pretty tight. It does in one place what I was doing in two. So I think that's OK. Let me go ahead and do Python of agree.py one last time. Let's try it one last time. And it's still working as intended. Also, if I tried those other inputs as well. Yeah, question. Let me summarize. Could we handle uppercase and lowercase together in some form? I'm actually doing that already. I just have to pick a lane. I have to either be all lowercase in my logic or all uppercase and not worry about what the human types in, because no matter what the human types in, I'm forcing their input to lowercase. And then I am using a lowercase list of values. If I want to flip that, fine. I just have to be self-consistent. But I'm handling that already. Yeah? A really good loaded question. Are strings no longer an array of characters? Conceptually, yes. Underneath the hood, no. They're a little more sophisticated than that. Because with strings, you have a few changes. Not only do they have functions built into them, because strings are now what we call objects in what's called object-oriented programming. And we're going to keep seeing examples of this dot operator. They are also immutable, so to speak. I-M-M-U-T-A-B-L-E. Immutable means they cannot be changed, which means unlike C, you can't go into a string and change its individual characters. You can make a copy of the string that makes a change, but you can't change the original string itself. This is both a little annoying maybe sometimes, but it's also pretty protective because you can't do screw-ups like I did weeks ago when I was trying to copy S and call it T, and then one affected the other. Python underneath the hood is handling all of the memory management and the pointers and all of that. There are no pointers in Python. So if that wasn't clear, all of that pain, if you will, all of that power is now handled by the language itself, not by us, the programmers. All right, so let's introduce maybe some loops like we've been in the habit of doing. Let me open up meow.c, which was an example in C, just meowing a bunch of times textually. Let me create a file called meow.py here on the right. And notice on the left, this was correct code in C, but it was kind of poorly designed. Why? Because it was a missed opportunity for a loop. Why say something 3 times when you can say it just once? So in Python, let me do it the poorly designed way first. Let me print out meow. And like I generally should not, let me copy paste it 3 times, run Python of meow.py, and it works. OK, but not good practice. So let me go ahead and improve this a little bit. And there's a few ways to do this. If I wanted to do this 3 times, I could instead do something like this. For I in range of 3, recall that that was the better version rather than arbitrarily enumerate numbers yourself. Let me go ahead and print out, quote unquote, meow. Now if I run Python of meow, still seems to work. So it's a little tighter. And my God, like programs can't really get much shorter than this. We're down to 2 lines of code, no main function, no gratuitous syntax. Let's now improve the design further like we did in C by introducing a function called meow that actually does the meowing. So this was our first abstraction, recall, both in Scratch and in C. Let me focus now entirely on the Python version here. Let me go ahead and first define a function Let me first go ahead and do this. For I in range of 3, let's assume for the moment that there's a meow function that I'm just going to call. Let's now go ahead and define, using the def keyword, which we saw briefly with the speller demonstration, a function called meow that takes no arguments, and all it does for now is print meow. Let me now go ahead and run Python of meow.py, enter. One of those tracebacks. So this is another name error. And again, name meow is not defined. What's your instinct here, even though we've not tripped over this yet in Python? Where does your mind go here? Yeah.
Since it reads top to bottom, left to right, it hasn't yet seen if you define a new
Perfect. As smarter as Python seems to be, it still makes certain assumptions. And if it hasn't seen a keyword yet, it just doesn't exist. So if you want it to exist, we have to be a little clever here. I could just flip it around like this. But this honestly isn't particularly good design. Why? Because now if you, the reader of your code, whether you wrote it or someone else, you kind of have to go fishing now. Like, where does this program begin? And even though, yes, it's obvious that it begins on line 4, logically, like if the file were longer, you're going to be annoyed and fishing visually for the right lines of code. So let's reintroduce main. And indeed, this would be a common paradigm when you want to start having abstractions and your own functions. Just put your own code in main so that 1, you can leave it up top, and 2, you can solve the problem we just encountered. So let me define a function called main that has that same loop meowing 3 times. But now watch what happens. Let me go into my terminal and run Python of meow.py, enter. Nothing. All right. Investigate this. What could explain this symptom? I have not told you the answer yet. So all you have is your instinct, assuming you've never touched Python before. What might explain this symptom where nothing is meowing? Yeah. Yeah, I didn't run the main function. So in C, this is functionality you get for free. You have to have a main function, but heck, so long as you make it, it will be called for you. In Python, this is just a convention to create a main function, borrowing a very common name for it. But if you want to call that main function, you have to do it. So this looks a little weird, admittedly, that you have to call your own main function now. And it has to be at the bottom of the file, because only once the interpreter gets to the bottom of the file have all of your functions been defined higher up. But this solves both problems. It keeps your code, that's the main part of your code, at the very top of the file. So it's just obvious to you and a TF or any reader in the future where the program logically starts. But it also ensures that main is not called until everything else, main included, has been defined. So this is another perfect example of we're learning a new language for the first time. You're not going to have heard all of the answers before. Just apply some logic as to, like, all right, what could explain this symptom? Start to infer how the language does or doesn't work. If I now go and run this, Python of meow.py, now we're back in business. And just so you have seen it, there is a quote unquote better way of doing this that solves different problems that we are not going to encounter, certainly in these initial days. Typically, you would see in online tutorials or books something that looks like this, where you actually have a weird conditional with multiple underscores. That's functionally the same thing, but it solves problems with libraries if we ourselves were implementing a library or something similar in spirit. But we're going to keep things simpler and just write main at the bottom, because we're not going to encounter that problem just yet. All right, let's make one change to this just to show how it's done. In C, the last version of meow also took arguments to the function meow. So suppose that I want to factor this out, and I want to just call meow as a better abstraction, where I just say meow this number of times. And I figure out how many times by just like putting in number 3 or using getInt or something like that to figure out how many times to say meow. Well, now I have to define inside my meow function in input, let's call it n, and then use that as by doing this. For I in range of n, let me go ahead and print out meow that many times. So again, the only thing that's different in C is we don't bother specifying return types for any of these functions, and we don't bother specifying the type of our arguments or our variables. So same ideas, simpler in some sense. We're just throwing away keystrokes. All right, let me run this one final time, Python of meow.py, and we still have the same program. All right, let me pause here. Any questions? And I know this is going fast, but hopefully the C code is still somewhat familiar. Yeah?
Is there any differences between global and local variables?
Good question. Is there any difference between global and local variables? Short answer, yes. And we would run into that same problem. If we declare a variable in one function, another function is not going to have access to it. We can solve that by putting variables globally. But we don't have all of the features we had in C. Like there's no such thing as a constant in Python. The mentality in the Python community is if you don't want some value to change, don't touch it. Like just don't screw up. So there's trade-offs here too. Some languages are stronger or more defensive than that. But that too is part of the mindset with this particular language. Yeah. Oh, sorry. Say it louder. That is an amazing segue. Let's come to that in just a moment, because we're going to recreate also that Mario example where we had like the question marks for the coins and the vertical bars. So let's come back to that in a second. And your question? Correct. Strings are immutable. Anytime you seem to be modifying it, as with the lower function, you're getting back a copy. So it's taking a little more memory somewhere, but you don't have to deal with it. Python's doing that for you. Say it again. You don't need what? You don't free anything. So if you weren't a big fan over the past couple of weeks of malloc or free or memory or addresses or all of those low-level implementation details, Python is the language for you because all of that is handled for you automatically. Java does the same. JavaScript does the same. Yeah? How do you define a global variable if there's no main function in Python? Global variables, by definition, always need to be outside of main as well. So that's not a problem. If I wanted to have a function that's outside of and therefore global to all of these, like global, actually, don't use the word global. That's a special word in Python. Variable equals foo. FOO, just as an arbitrary string value that a computer scientist would typically use, that is now global. There are some caveats, though, as to how you access that. But let's come back to that another time. But that problem is solvable, too. All right, so let's go ahead and do this to come back to the question about the print command. Let me go ahead and create a file now called mario.py. Won't bother showing the C code anymore. We'll focus just on the new language here. But recall that in Mario, we wanted to first do something like this. This was a random screen from the side scroller version 1 of Super Mario Brothers. And we just want to print like 3 hashes to represent those 3 blocks. Well, in Python, we could do something like this. Print, for I in the range of 3, go ahead and print out, quote unquote, hash. And I think this is pretty straightforward. Python of mario.py, we get our 3 hashes. You could imagine parameterizing this now, though, and getting actual user input. So let's do that. Let me go up here, and let me go and say from CS50 import get int. And then let's get the input from the user. So it actually is a value n. Like, all right, get int the height of the column of bricks that you want to do. And then let's go ahead and print out n hashes instead of 3. So let me run this. Let's print out like 5 hashes. OK, 1, 2, 3, 4, 5. That seems to work too. And it's going to work for any positive value. But it's not going to work for, how about -1? That just doesn't do anything. But that seems OK. But also recall that it's not going to work if the user types in something weird like it is going to work if the user types in something weird like cat. Why? We're using CS50's getInt function, which is handling all of those headaches for us. But what if the user indeed types a negative number? We're tolerating that. So that was the bug I wanted to highlight. It would be nice to reprompt them and reprompt them. And in C, what was the programming construct we used when we wanted to ask the user a question, and then if they didn't cooperate, prompt them again, prompt them again? What was that? Yeah, do while loop, right? That was useful because it's almost the same as a while loop. But instead of checking a condition and then doing something, you do something and then check a condition, which makes sense with user input because what are you even going to check if the user hasn't done anything yet? You need that inverted logic. Unfortunately, in Python, there is no do while loop. There is a for loop. There is a while loop. And frankly, those are enough to recreate this idea. And the way to do this in Python, the Pythonic way, which is another term of art in the community, is to say this. Deliberately induce an infinite loop while true, with capital T for true, and then do what you got to do, like get an int from a user, asking them for the height of this thing, and then if that is what you want, like a number greater than 0, go ahead and break out of the loop. So this is how, in Python, you could recreate the idea of a do-while loop. You deliberately induce an infinite loop, so something's going to happen at least once. Then, if you get the answer you want, you break out of it, effectively achieving the same logic. So this is the Pythonic way of doing a do-while loop. Let me go ahead and run Python of Mario.py, type in 3 this time, and now I get back just the 3 hashes as well. What if, though, I wanted to get rid of how about ultimately that CS50 library function and also encapsulate this in a function? Well, let's go ahead and tweak this a little bit. Let me go ahead and remove this temporarily, give myself a main function so I don't make the same mistake as I did initially earlier. And let me give myself a function called getHeight that takes no arguments. And inside of that function is going to be that same code. But I don't want to break in this case. I want to return n. So recall that if you return from a function, you're done. You're going to exit from right that point. So this would be fine. You can just say return n inside of the loop. Or if you would prefer to break out, you could do something like this instead. Break. And then down here, you could return n as well. And let me make one point here before we go back up to main. This is a little different from C. And this one's subtle. What have I done here that in C would have been a bug, but is apparently not, I claim, in Python? It's super subtle, this one. Yeah? So similar. It's not quite that we're using it first. So it's OK not to declare a variable with like the data type. We've addressed that before. But on line 9, we're assigning n a value, it seems. And then we return n on line 12. But notice the indentation. In the world of C, if we had declared a variable inside of a loop on line 9, it would have been scoped to that loop, which means as soon as you get out of that loop, like further down in the program, n would not exist. It would be local to the curly braces therein. Here, logically, curly braces are gone, but the indentation makes clear that n is still inside of this loop between lines 8 through 11. But n is actually still in scope in Python. The moment you create a variable in Python, for better or for worse, it is available everywhere within that function, even outside of the loop in which you defined it. So this logic is actually OK in Python. In C, recall, to solve this same problem, we would have had to do something a little hackish like this, like define n up here on line 8 so that it exists now on line 10 and so that it exists on line 13. That is no longer an issue or need in Python. Once you create a variable, even if it's nested, nested, nested inside of some loops or conditionals, it still exists within the function itself. All right. Any questions then on this before we now run this and then get rid of the CS50 library again? OK, so let me go ahead and get the height from the user. Let's go ahead and create a variable in main called height. Let's call this getHeight function. And then let's use that height value instead of something hard-coded there. And let me see if this all works now. Python of Mario.py. Hopefully I haven't messed up, but I did. But this is an easy fix now. Yeah. I got to call main. So again, I deleted that earlier, but let me bring it back. So I'm actually calling main. Let me rerun Python of Mario.py. There we go. Height 3. Now it seems to be working. So let's do one last thing with Mario just to tie together that idea now of exceptions from before. Again, exceptions are a feature of Python whereby you can try to do something. And if there's a problem, you can handle it in any way you see fit. Previously, I handled it by just yelling at the user that that's not an int. But let's actually use this to re-implement CS50's own getInt function. Let me throw away CS50's getInt function. And now let me go ahead and replace getInt with input, but it's not sufficient to just use input. What do I have to add to this line of code on line 8? If I want to get back an int? Yeah, I have to cast it to an int by calling the int function around that value. Or I could do it on a separate line, just to be clear. I could also do n equals int of n. That would work too, but it's sort of an unnecessary extra line. This is not sufficient because that does not change the value. It creates the value, but then it throws it away. You need to assign it. So the conventional way to do this would probably be in one line just to keep things nice and tight. So that works fine now. If I run Python of mario.py, I can still type in 3 and all is well. I can still type in -1 because that is an int that I am handling. What I'm not yet handling is weird input like cat or some string that is not a base 10 number. So here again is my traceback. And notice that here, let me scroll up a little bit. Here we can actually see more detail in the traceback. Notice that just like in C, or just like in the debugger in VS Code, you can see a few things. You can see mention of module. That just means your file. Main, which is my main function, and get height. So notice it's kind of backwards. It's top to bottom instead of bottom up as we drew it on the board the other day and as we envisioned stacks of trays in the cafeteria. But this is your stack of functions that have been called from top to bottom. Get height is the most recent. Main is the very first. Value error is the problem. So let's try to do this literally, except if there's an error. So what do I want to do? I'm going to go in here and I'm going to say try to do the following. Whoops. Try to do the following, except if there's a value error, then go ahead and say something like, well, like before, print that's not an integer, exclamation point. But the difference this time is because I'm in a loop, the user's going to have a chance to recover from this issue. So if I run mario.py, 3 still works as before. If I run mario.py and type in cat, I detect it now. And because I'm still in that loop, and because the program hasn't crashed, because I've caught, so to speak, the value error using this line of code here, that's the way in Python to detect these kinds of errors that would otherwise end up being on the user's own screen. If I type in cat, dog, that doesn't work. If I type in, though, 2, I get my 2 hashes, because that's indeed an int. All right, any questions on this? And we're not going to spend too much time on exceptions, but just wanted to show you what's involved with getting rid of those training wheels. Yeah? OK, so let's do this. That actually comes to the earlier question about printing the hashes on the same line, or maybe something like this, where we have little bricks in the sky or little question marks. Let's recreate this idea, because the problem with print, as was noted earlier, is you're automatically printing out new lines. But what if we don't want that? Well, let's change this program entirely. Let me throw away all the functions. Let's just go to a simpler world where we're just doing this. So let me start fresh in mario.py. I'm not going to bother with exceptions or functions. Let's just do a very simple program to create this idea. For I in range of 4 this time, because there are 4 of these things in the sky. Let's go ahead and just print out a question mark to represent each of those bricks. Odds are, you know this is not going to end well, because these are unfortunately, as you predicted, on separate lines. So it turns out that the print function actually takes in multiple arguments, not just the thing you want to print, but also some additional arguments that allow you to specify what the default line ending should be. But what's interesting about this is that if you want to change the line ending to be something like quote unquote, that is nothing, instead of \n, this is not sufficient, because in Python you can have 2 types of arguments or parameters. Some arguments are positional, which is the fancy way of saying it's a comma-separated list of arguments. And that's what we did all the time in C. Something, comma, something, comma, something. We did it in printf all the time and in other functions that took multiple arguments. In Python, you have not only positional arguments, where you just separate them by commas to give 1 or 2 or 3 or more arguments. There are also named arguments, which looks weird but is helpful for reasons like this. If you read the documentation, you will see that there is a named argument that Python accepts called end. And if you set that equal to something, that will be used as the end of every line instead of the default, which the documentation will also say is quote unquote \n. So this line here has no effect on my logic at the moment. But if I change it to just quote unquote, essentially overriding the default new line character and now run Mario again, now I get all 4 on the same line. There's a bit of a bug, though. My prompt is not meant to be on the same line. So I can fix that by just printing nothing. But really, it's not nothing, because you get the new line for free. So let me run Python of mario.py again. And now we have what I intended in the first place, which was a little something that looked like this. And this is just one example of an argument that has a name. But this is a common paradigm in Python 2 to not just separate things by commas, but to be very specific, because the print function might take 5, 10, even 20 different arguments. And my God, if you had to enumerate like 10 or 20 commas, you're going to screw up. You're going to get things in the wrong order. Named arguments allow you to be resilient against that. So you only specify arguments by name, and it doesn't matter what order they are in. All right, any questions then on this and the overriding of new line? And to be clear, you can do something like very weird, but logically expected like this by just changing the line ending too. But the right way to solve the Mario problem would be just to override it to be nothing like this. All right, how about this for cool? And this is why a lot of people like Python. Suppose you don't really like loops. You don't really like 3-line programs, because that was kind of 3 times longer than it needs to be. What if you just printed out a question mark 4 times? Python of mario.py, that also works. So it turns out that just like the plus operator in Python can join things together, the multiply operator is not arithmetic in this case. It actually means take this and concatenate it 4 times over. So that's a way of just distilling into one line what would have otherwise taken multiple lines in C, fewer, but still multiple lines in Python, but is really now rather succinct in Python by doing that instead. Let's do one last Mario example, which looked a little something like this. If this is another part of the Mario interface, this is like a grid of like 3 by 3 bricks, for instance. So 2 dimensions now, not just vertical, not horizontal, but now both. Let's print out something like that using hashes. Well, how do I do this? So how about for I in range of 3? Then I could do for j in range of 3, just because j comes after I, and that's reasonable for counting. I could now print out a hash symbol. Well, let's see what this does. Python of mario.py. OK, that's just one crazy long column. What do I need to fix and where here to make this look like this? So 3 by 3 bricks instead of one long column. Any instincts? OK, so after printing 3, we want to skip a line. So maybe like print out a blank line here. OK, let's try that. I like that instinct, right? Print 3, new line. Print 3, new line. Let's go ahead and run Python of mario.py. OK, it's more visible what I'm doing, but still wrong. What's the remaining fix, though? Yeah. Yeah, I'm getting an extra new line here, which I don't want while I'm on this row. So let me do end equals quote unquote. And now together, your solutions might take us the whole way there. Python of mario.py. Voila, now we've got it in 2 dimensions. And even this, we can tighten up. Like, we could just use the little trick we learned. So we could just say print a hash times 3 times. And we can get rid of one of those loops altogether. All it's doing is automating that process. But no, I don't want to do that. How do I fix this here? Oh, I don't think I want this anymore, right? Because that's giving me an extra new line. So now this program is really tightened up. Same thing, 2 lines of code, but we're now implementing this same 2-dimensional structure here. All right, any questions here on these? Yeah?
Is there any actual reason why whenever you write the print function, you don't put any spaces in it?
If print n, any spaces. Say that once more.
Whenever you write n, for example, the print function, in order to stop it from going to a new line, you didn't put any spaces in between it, like n equals and then 2 quotes. There were no spaces. Did you do that on purpose?
Oh, yes, good question. I see what you're saying. So in a previous version, let me rewind in time. When we had this, I did not put spaces. The convention in Python is not to do that. Why? It just starts to add too much space. And this is a little inconsistent, because earlier when we talked about like pluses or spaces around the less than or equal signs, I did say add it. Here, it's actually clearer and recommended to keep them tighter together. Otherwise, it just becomes harder to read where the gaps are. Good observation. All right, let's do, how about another 5-minute break. Let's do that. And then we're going to dive into some more sophisticated problems and then ultimately build with some audio and visual examples as well. See you in 5. So almost all of the examples we just did were recreations of what we did in week 1. And recall that week 1 was like our most syntax heavy week. It was when we were first learning how to program in C. But after week 1, we began to focus a bit more on ideas like arrays and other higher level constructs. And we'll do that again here, condensing some of those first early weeks into a fewer set of examples in Python. And we'll culminate by actually taking Python out for a spin and doing things that would be way harder to do and way more time consuming to do in C, even more so than the speller example. But how do you go about figuring out like what functions exist? If you didn't hear it in class, you don't see it online, but you want to see it officially, you can go to the Python documentation, docs.python.org here. And I will disclaim that, honestly, the Python documentation is not terribly user-friendly. Google will often be your friend, so Googling something you're interested in to find your way to the appropriate page on python.org, or stackoverflow.com is another popular website. As always, though, the line should be Googling things like, how do I convert a string to lowercase? Like, that's reasonable to Google. Or how to convert to uppercase. Or how implement function in Python. But Googling, of course, things like how to implement problem set 6 in CS50, of course, crosses the line. But moving forward, and really with programming in general, like Google and Stack Overflow are your friends, but the line is between the reasonable and the unreasonable. So let me officially use the Python documentation search just to search for something like the lowercase function. Like, I know I can lowercase things in Python. I don't quite remember how. So let me just search for the word lower. You're going to get often an overwhelming number of results, because Python's a pretty big language with lots of functionality. And you're going to want to look for familiar patterns. For whatever reason, string.lower, which is probably more popular or more commonly used than these other ones, is third on the list. But it's purple because I clicked it a moment ago when looking for it. So str.lower is probably what I want, because I am interested at the moment in lowercasing strings. When I click on that, this is an example of what Python's documentation tends to look like. It's in this general format. Here's my str.lower function. This returns a copy of the string with all of the cased characters converted to lowercase, and the lowercasing algorithm, ... So that doesn't give me much. It doesn't give me sample code, but it does say what the function does. And if we keep looking, you'll see mention of lstrip, which is left strip. I used its analog rstrip before. Right strip, which allows you to remove, that is, strip from the end of a string, something like white space, like a new line, or even something else. And if you scroll through string, this web page here, and we're halfway down the page already, if you see my scroll bar tiny on the right, there's a huge amount of functionality built into string objects here. And this is just testament to just how rich the language itself is. But it's also reason to assure that the goal when playing around with some new language and learning it is not to learn it exhaustively. Just like in English or any human language, there's always going to be vocab words you don't know, ways of presenting the same information in some language. That's going to be the case with Python. And what we'll do today and this week in problem set 6 is really get your footing with this language. But you won't know all of Python, just like you won't know all of C. And honestly, you won't know all of any of these languages on your own unless you're perhaps using them full-time professionally. And even then, there's more libraries than one might even retain themselves. So let's actually now pivot to a few other ideas that we'll implement in Python. In a moment, let me switch back over to VS Code here. And let me whip up, say, a recreation of our scores example from week 2, where we averaged like 3 scores together. And that was an opportunity in week 2 to play with arrays, to realize how constrained arrays are. They can't grow or shrink. You have to decide in advance. But let's see what's different here in Python. So let me do scores.py. And let me give myself an array in Python called scores. Sorry, let me give myself a variable in Python called scores. Set it equal to a list of 3 scores, which are the same ones we've used before, 72, 73, 33. In this context, meant to be scores, not ASCII values. And then let's just do the average of these. So average will be another variable. And it turns out I can do, well, how did I sum these before? I probably had a for loop to add 1. Then I knew how long there were. Turns out in Python, you can just say sum of scores divided by the length of scores. That's going to give me my average. So sum is a function that takes a list, in this case, as input, and it just does the sum for you with a for loop or whatever underneath the hood. Lang gives you the length of the list, how many things are in it, so I can dynamically figure that out. Now let me go ahead and print out, using print, the word average, and then in curly braces, the actual average, close quote. All right, so let's run this code, python of scores.py. And there's my average, in this case, 59.33333, and so forth, based on the math. Well, let's actually now change this a little bit and make it a little more interesting and actually get input from the user rather than hard coding this. Let me go back up here. and use from CS50 import get int, because I don't want to deal with all the exceptions and the loops. Like, I just want to use someone else's function here. Let me give myself an empty list called scores. And this is not something we were able to do in C, right? Because in C, if you tried to make an empty array, well, that's pretty stupid because you can't add things to it. It's a fixed size, so it wouldn't even let you do that. But I can just create an empty list in Python, because lists, unlike arrays, are really linked lists. They'll grow and shrink. But you and I are not dealing with all the pointers underneath the hood. Python's doing that for us. So now let's go ahead and get a whole bunch of scores from the user. How about 3 of them in total? So for I in range of 3, let's go ahead and grab a score from the user using getInt, asking them for score. And then let's go ahead and append to the scores list that particular score. So it turns out that a list, and I could read the Python documentation to confirm as much, lists have a function built into them. And functions built into objects are generally known as methods, if you've heard that term before. Same idea, but whereas a function kind of stands on its own, a method is a function built into an object, like a list here. That's going to achieve the same result. Strictly speaking, I don't need the variable. Just like in C, I could tighten this up and do something like this as well. But I don't know. I kind of like it this way. It's more clear, to me at least, that what I'm doing here, getting the score and then appending it to the list. Now the rest of the code can stay the same. Python of scores.py, score will be 72, 73, 33, and I get back the math. But now the program's a little more dynamic, which is nice. But there's other syntax I could use here, just so you've seen it. Python does have some neat syntactic tricks, whereby if you don't want to do scores.append, you can actually say scores plus equals this score. So you can actually concatenate lists together in Python too. Just as we use plus to join 2 strings together, you can use plus to join 2 lists together. The catch is you need to put the one score I'm adding here in a list of its own, which is kind of silly, but it's necessary so that this thing and this thing are both lists. To do this more verbosely, which most programmers wouldn't do, but just for clarity, this is the same thing as saying scores plus this score. So now maybe it's a little more clear that scores and bracket score, plural, sorry, singular, are both lists themselves, being concatenated or joined together. So 2 different ways. I'm not sure one is better than the other. This way is pretty common, but .append is also quite reasonable as well. All right. How about another example from week 2? This one was called uppercase. So let me do this in uppercase.py, though, this time. And let me import from CS50 getString again. And let me go ahead and say before will be my first variable. Let me get a string from the user, asking them for a before string. And then let me go ahead and say after, just to demonstrate some changes, uppercasing to this string. Let me change my line ending to be that using our new trick. And this is where things get cool in Python, relatively speaking. If I want to iterate over all of the characters in a string and print them out in uppercase, one way to do that would be this. For C in the before string, go ahead and print out C.uppercase, sorry, C.upper, but don't end the line yet because I want to keep these all on the same line until I'm all done. So what am I doing? Python of uppercase.py, let me type in hello in all lowercase. I've just uppercased the whole string. How? I first get string, calling it before. I then just print out some fluffy text that says after colon, and I get rid of the line ending just so I can kind of line these up. Notice I hit the space bar a couple times just so letters line up to be pretty. For C and before. This is new. This is powerful in in Python, whereby you don't have to do like int I equals 0 and I less than this. You could just say for C in the string in question, for C and before. And then here is just uppercasing that specific character and making sure we don't output a new line too soon. But this is actually more work than I need to do. Based on what we've seen thus far, like from our agreement example, can I tighten this up further? Can I collapse lines 5 and 6, maybe even 7 altogether? The goal of this program is just to uppercase the before string. How might I do this? Yeah, and back? Stir.upper, yeah. So I could do something like this. After gets before dot upper. So it's not stir literally dot upper. Stir just represents the string in question. So it would be before dot upper, but right idea otherwise. And so let me go ahead and just tweak my print statement a little bit. Let me just go ahead and print out the after variable here after creating it. So this line is the same. I'm getting a string called before. I'm creating another variable called after. And as you propose, I'm calling upper on the whole string, not one character at a time. Why? Because it's allowed. And again, in Python, there aren't technically characters individually. There's only strings anyway, so I might as well do them all at once. So if I rerun the code now, Python of uppercase.py, now I'll type in hello in all lowercase. And oh, so close. I think I can get rid of this override because I'm printing the whole thing out at once, not character by character. So now if I type in hello before, now I have an even tighter version of the program here. All right, any questions then on lists or on strings and what this kind of function upper represents with its docs? No? All right, so a couple other building blocks before we start. Oh, where was that? Then to the right. The right. Yes, thank you. Yes, do I have to create this variable upper? No, I don't. I could actually tighten this up. And if you really want to see something neat, inside of the curly braces, you don't have to just put the names of variables. You can put a small amount of logic, so long as it doesn't start to look stupid and kind of overwhelmingly complex, such that it's sort of bad design at that point. I can tighten this up like this and now run Python of uppercase.py, writing hello again. And that too worked. But I would be careful about this. You want to resist the temptation of having like a long line of code that's inside the curly braces, because it's just going to be harder to read. But absolutely, you could indeed do that too. All right, how about command line arguments, which was one thing we introduced in week 2 also, so that we could actually have the ability to take input from the user. So we could actually take input from the user at the command line so as to take literally command line arguments. These are a little different, but it follows the same paradigm. There's no main by default, and there's no def main int argc char, or we called it string argv by default. There's none of this. So if you want access to the argument vector, argv, you import it. And it turns out there's another module in Python, or library in Python, called sys. And you can import from the system this thing called argv. So same idea, different place. Now I'm going to go ahead and do this. Let's write a program that just requires that the user types in a word after the program's name or none at all. So if the length of argv equals 2, let's go ahead and print out, how about hello, comma, argv bracket 1, close quote. Else, if they don't type 2 words total at the prompt, let's just say the default, like we did weeks ago, hello world. So the only thing that's new here is we're importing argv from sys, and we're using this fancy f-string format, which kind of, to your point too, it's putting more complex logic in the curly braces, but that's OK. In this case, it's a list called argv, and we're getting bracket 1 from it. Let's do Python of argv.py, enter, hello world. What if I do argv.py David at the command line? Now I get hello David. So there's one curiosity here. Python is not included in argv, whereas in C, /whatever was the first thing. The analog in Python is that the name of your Python program is the first thing. In bracket 0, which is why David is in bracket 1, the word Python does not appear in the argv list, just to be clear. But otherwise, the idea of these arguments is exactly the same as before. And in fact, what you can do, which is kind of cool, is because argv is a list, you can do things like this. For arg in argv, go ahead and print out each argument. So instead of using a for loop and I and all of this, if I do Python of argv enter, it just writes the program's name. If I do Python of argv foo, it puts argv.py and foo. If I do foo and bar, those words all print out. If I do foo bar baz, those print out too. And foo and bar or baz are like a mathematician's x and y and z for a computer scientist when you just need some placeholder words. So this is just nice. It reads a little more like English, and a for loop is just much more concise. Allows you to iterate very quickly when you want something like that. Suppose I only wanted the real words that the human typed after the program's name. Like suppose I want to ignore argv.py. I mean, I could do something hackish like this. If arg equals argv.py, I could just ignore, let's invert the logic. I could do this, for instance. So if the arg does not equal the program name, then go ahead and print out the word. So I get foo bar and baz only. Or this is what's kind of neat about Python 2. Let me undo that. And let me just take a slice of the array of the list instead. So it turns out if argv is a list, I can actually say, you know what, go into that list, start at element 1 instead of 0, and then go all the way to the end. And we have not seen the syntax in C, but this is a way of slicing a list in Python. So now watch what happens. If I run python of argv.py, foo, bar, baz, enter, I get only a subset of the list starting at position 1, going all the way to the end. And you can even do kind of the opposite. If for whatever reason you want to ignore the last element, you can say colon, we could say colon -1 and use a negative number, which we've not seen before, which slices off the end of the list as well. So there's some syntactic tricks that tend to be powerful in Python 2, even if at first glance you might not need them for typical things. All right, let's do one other example with exit. And then we'll start actually applying some algorithms to make things interesting. So in one last program here, let's do exit.py just to do one more mechanic before we introduce some algorithms. And let's do this. Let's import from sys import argv. Let's now do this. Let's make sure the user gives me one command line argument. So if the length of argv does not equal 2 in total, then let's go ahead and print out something like missing command line argument, just to explain what the problem is. And then let's do this. We can exit. But I'm going to use a better version of exit here. Let me import 2 functions from sys. Turns out the better way to do this is with sys.exit, because I can then exit specifically 2 with this exit code. Otherwise, down here, I'm going to go ahead and print out something like hello, comma, argv bracket 1, same as before, and then I'm going to exit with 0. So again, this was a subtle thing we introduced in week 2, where you could actually have your programs exit with some number where 0 signifies success and anything else signifies error. This is just the same idea in Python. So if I, for instance, just run the program like this, oops, I screwed up. I meant to say exit here and exit here. Let me do that again. If I run this like this, I'm missing a command line argument. So let me rerun it with like my name at the prompt. So I have exactly 2 command line arguments, the file name and my name, hello, comma, David. And if I do David Malin, it's not going to work either, because now argv does not equal 2. But the difference here is that we're exiting with 1 so that special programs can detect an error, or 0 in the event of success. And now there's one other way to do this too. Suppose that you're importing a lot of functions and you don't really want to make a mess of things and just have all of these function names available without it being clear where they came from. Let's just import all of sys. And let's just change our syntax, kind of like I proposed for CS50, where we just prepend to all of these library functions sys, just to be super explicit where they came from. And if there's another exit or argv value that we want to import from a library, this is one way to avoid collision. So if I do it one last time here, missing command line argument, but David still actually works. All right, only to demonstrate how we can implement that same idea. Let's now do something more powerful, like a search algorithm, like binary search. I'm going to go ahead and open up a file called numbers.py, and let's just do some searching, or linear search, rather, on a list of numbers. Let's go ahead and do this. How about import sys as before? Let me give myself a list of numbers, like 4, 6, 8, 2, 7, 5, 0. So just a bunch of integers. And then let's do this. If you recall from week 3, we searched for the number 0 at the end of the lockers on stage. So let's just ask that question in Python. No need for a loop or anything like that. If 0 is in the numbers, go ahead and print out found. And then let's just exit successfully with 0. Else, if we get down here, let's just say print not found. And then we'll sys exit with 1. So this is where Python starts to get powerful again. Here's your list. Here is your loop that's doing all of the checking for you. Underneath the hood, Python's going to use linear search. You don't have to implement it yourself. No while loop, no for loop. You just ask a question. If 0 is in numbers, then do the following. So that's one feature we now get with Python, and get to throw away a lot of that code. We can do it with strings too. Let me open a file called names.py instead, and do something that was even more involved in C, because we needed stir comp and the for loop and so forth. Let me import sys for this file. Let's give myself a bunch of names like we did in C. And those were Bill and Charlie and Fred and George and Ginny and 2 more, Percy And lastly, Ron. And recall at the time we looked for Ron, and so we had to iterate through the whole thing, doing strcomp and I++ and all of that. Now just ask the question. If Ron is in names, then let's go ahead and, whoops, let me hide that. I hit the command too soon. Let me go ahead and say print found, as before, sysexit1 just to indicate success. And then down here, if we get to this point, we can say not found. And then we'll just sysexit1 instead. So again, this just does linear search for us by default. Python of names.py, we found Ron, because indeed he's there and at the end of the list. But we don't need to deal with all of the mechanics of it. All right, let's take things one step further. In week 3, we also implemented the idea of a phone book that actually associated keys with values. But remember, the phone book in C was kind of a hack, right? Because we first had 2 arrays, one with names, one with numbers. Then we introduced structs, and so we gave you a person structure. And then we had an array of persons. You can do this in Python using objects and things called classes. But we can also just use a general purpose dictionary, because just like in pset5, you can associate keys with values using a hash table, using a trie. Well, similarly, can Python just do this for us? From CS50, let's import getString. And now let's give myself a dictionary of people. DICT, open paren, close paren, gives you a dictionary. Or you can simplify the syntax, actually. And a dictionary, again, is just keys and values, words and definitions. You can also just use curly braces instead. That gives me an empty dictionary. But if I know what I want to put in it by default, let's put Carter in there with a number of +1, 617, 495, 1000, just like last time. And put myself, David, with +1, 949, 468. 2750. And it came to my attention tragically after class that day that we had a bug in our little Easter egg. If today you would like to call me or text me at that number, we have fixed the code that underlies that little Easter egg. Spoiler ahead. All right, so this now gives me a variable called people that's associating keys with values. There is some new syntax here in Python, not just the curly braces, but the colons and the quotes on the left and the right. This is a way in Python of associating keys with values, words with definitions, anything with anything else. And it's going to be a super common paradigm, including in week 7, when we look at CSS and HTML and web programming. Keys and values are like this omnipresent idea in computer science and programming, because it's just a really useful way of associating one thing with another. So at this point in the story, we have a dictionary, a hash table, if you will, of people, associating names with phone numbers, just like a real-world phone book. Let's write a program that gets a string from the user and asks them whose number they would like to look up. Then let's go ahead and say, if that name is in the people dictionary, go ahead and print out that person's number by going into the people dictionary and going to that specific name within there, using an F string for the whole thing. So this is similar in spirit to before. Linear search and dictionary lookups will just happen automatically for you in Python by just asking the question, if name and people. And this line's just going to print out whoever is in the people dictionary at that name. So I'm using square brackets, because here's the interesting thing in Python. Just like you can index into an array or a list in Python using numbers, 0, 1, 2, you can very conveniently index into a dictionary in Python using square brackets as well. And just to make clear what's going on here, let me go and create a temporary variable, person equals people bracket name. And then let's say number equals people bracket name. And let's just print out the number in question. In C and previously in Python, anything with square brackets like this would have been go to a location in a list or an array using a number. But that can actually be a string, like a word the human has typed. And this is what's amazing about dictionaries. It's not like a big line of a big linear thing. It's this table that you can look up in one column the name and get back in the other column the number. So let's go ahead and run Python of phonebook.py. Found, not that, oh wait. That's not what's supposed to happen at all. I think I'm in the wrong play. Phonebook.py. What's going on? Print found. I am confused. OK. Let's run this again. Python of phonebook.py. What the? OK, stand by. What the hell? What am I not understanding here? OK, Rongxin, Carter, do you see what I'm doing wrong? What the? Say again? Oh, what? Yeah. Found. OK, we're going to do this. One sec. Whoa. OK. All this is coming out of the video. Thanks. All right. I will try to figure out what was going wrong. The best I can tell, it was running the wrong program. I don't quite understand why, so we will diagnose this later. I just put the file into a temporary directory for now to run it. So let me go ahead and just run this, Python of phonebook.py. Type in, for instance, my name, and there's my corresponding number. I have no idea what was just happening, but I will get to the bottom of it and update you if we can put our finger on it. So this was just an example now of implementing a phone book. Let's now consider what we can do that's a little more powerful in these examples, like a phone book that actually keeps this information around. Thus far, these simple phone book examples throw the information away. But using CSV files, comma-separated values, maybe we could actually keep around the names and numbers so that, like on your phone, you can actually keep your contacts around long term. So I'm going to go ahead now and do a slightly different example. And let me just hide this detail so it's not confusing. Whoops. I'm going to change my prompt temporarily. So let me go ahead now and refine this example as follows. I'm going to go into phonebook.py, and I'm going to import a whole library called CSV. And this is a powerful one because Python comes with a library that just handles CSV files for you. A CSV file is just a file with comma-separated values. And in fact, to demonstrate this, let me check on one thing here just to make this a little more real. To demonstrate this, let's go ahead and do this. Let me import the CSV library. From CS50, let me import getString. Let me then open a file using the open function. Open a file called phonebook.csv in append format, in contrast with read format and write format. Write just blows it away. If it exists, append adds to the bottom of it. So I keep this phone book around, just like you might keep adding contacts to your phone. Now let me go ahead and get a couple values from the user. Let me say getString and ask the user for a name. Then let me get string again and ask the user for their number. And now let me go ahead and do this. And this is new, and this is Python specific. And you would only know this by following a tutorial or reading the documentation. Let me give myself a variable called writer and ask the CSV library for a writer to that file. Then let me go ahead and use that writer variable, use a function or a method inside of it called writeRow to write out a list containing that person's name and number. Notice the square brackets inside the parentheses because I'm just printing a list to that particular row in the file. And then I'm just going to close the file. So what is the effect of all of this? Well, let me go ahead and run this version of phonebook.py, and I'm prompted for a name. Let's do Carter's first, +1, 617, 495, 1000. And then let's go ahead and ls. Notice in my current directory, there's two files now, phonebook.py, which I wrote, and apparently phonebook.csv. CSV just stands for comma-separated values, and it's like a very simple way of storing data in a spreadsheet, if you will, where the comma represents the separation between your columns. There's only two columns here, name and number. But because I'm writing to this file in append mode, let me run it one more time, Python of phonebook.py. And let me go ahead and do David and +1, 949, 468, 2750, enter. And notice what happened in the CSV file. It automatically updated because I'm now persisting this data to the file in question. So if I wanted to now read this file in, I could actually go ahead and do linear search on the data using a read function to actually read from the CSV. But for now, we'll just leave it a little simply as write. And let me make one refinement here. It turns out that if you're in the habit of opening a file, you don't have to even close it explicitly. You can instead do this. You can instead say, with the opening of a file called phonebook.csv in append mode, calling the thing file, go ahead and do all of these lines here. So the with keyword is a new thing in Python, and it's used in a few different ways. But one of the ways it's used is to tighten up code here. And I'm going to move my variables to the outside because they don't need to be inside of the with statement where the file is opened. This just has the effect of ensuring that you, the programmer, don't screw up and accidentally don't close your file. In fact, you might recall from C, Valgrind might have complained at you if you had a file that you didn't close a file. You might have had a memory leak as a result. The with keyword takes care of all of that for you as well. How about, do we want to do this? How about, let's do one other thing. Let's do this. Let me go ahead and propose that on your phone or laptop here or online, go to this URL here, where you'll find a Google form. And just to show that these CSVs are actually kind of omnipresent. And if you've ever used a Google form or managed a student group or something where you've collected data via Google Forms, you can actually export all of that data via CSV files. So go ahead to this URL here. And those of you watching on demand later will find that the form's no longer working since we're only doing this live. But that will lead to a Google form that's going to let everyone input their answer to a question like, what house do you want to end up into? Sort of an approximation of the sorting hat in Harry Potter. And via this form, will we then have the ability to export, we'll see, a CSV file. So let's give you a moment to do that. In just a moment, I'll share my version of the screen, which is going to let me actually open the file, the form itself. And in just a moment, I'll switch over. My internet here is being slow. Come on. Come on. OK. Stand by. I will switch over in a moment once I have access. Sorry. Give me 1 second. All right. And in a moment, oh my God, so many steps today. Let's go to the same URL. OK, so this is now my version of the form here, where we have 200 plus responses to a simple question of the form, what house do you belong in? Gryffindor, Hufflepuff, Ravenclaw, or Slytherin? If I go over to responses, I'll see all of the responses in the GUI form here. So graphical user interface. And we could flip through this, and it looks like, interestingly, 40% of Harvard students want to be in Gryffindor. 22% in Slytherin, and everyone else in between the others. But you might have noticed, if ever using a Google form, this Google Spreadsheets link. So I'm going to go ahead and click that, and that's going to automatically open, in this case, Google Spreadsheets. But you can do the same thing with Office 365 as well. And now you see the raw data as a spreadsheet. But in Google Spreadsheets, if I go to File, and then I go to Download, notice I can download this as an Excel file, a PDF, and also a CSV, comma-separated values. So let me go ahead and do that. That gives me a file in my Downloads folder on my computer. I'm going to now go back to my code editor here. And what I'm going to go ahead and do is upload this file from my Downloads folder to VS Code so that we can actually see it within here. And now you can see this open file. And I'm going to shorten its name just so it's a little easier to read. I'm going to rename this using the mv command to just hogwarts.csv. And then we can see in the file that there's 2 columns, timestamp column house, where you have a whole bunch of timestamps when people filled out the form, someone very early in class, and then everyone else just a moment ago. And the second value after each comma is the name of the house. Well, let me go ahead here and implement a program in a file called hogwarts.py that processes this data. So in hogwarts.py, let's just write a program that now reads a CSV, in this case not a phone book, but everyone's sorting hat information. And I'm going to go ahead and import CSV. And suppose I want to answer a reasonable question, ignoring the fact that Google's GUI, or graphical user interface, can do this for me. I just want to count up who's going to be in which house. So let me give myself a dictionary called houses that's initially empty with curly braces. And let me pre-create a few keys. Let me say Gryff indoor is going to be initialized to 0. Hufflepuff will be initialized to 0 as well. Ravenclaw will be initialized to 0. And finally, Slytherin will be initialized to 0. So here's another example of a dictionary or a hash table just being a very general purpose piece of data. You can have keys and values. The keys in this case are the houses. The values are initially 0, but I'm going to use this instead of like 4 separate variables to keep track of everyone's answer to this form. So I'm going to do this with opening Hogwarts.csv in read mode, not append. I don't want to change it. I just want to read it as file, as my variable name. Let's go ahead and create a reader this time that is using the reader function in the CSV library by opening that file. I'm going to go ahead and ignore the first line of the file, because recall that the first line is just timestamp and house. I want to get the real data. So this next function is just a little trick for ignoring the first line of the file. Then let's do this. For every other row in the reader, that is line by line, get the current person's house, which is in row bracket 1. This is what the CSV reader library is doing for us. It's handling all of the reading of this file. It figures out where the comma is. And for every row in the file, it hands you back a list of size 2. In bracket 0 is the timestamp. In bracket 1 is the house name. So in my code, I can say house equals row bracket 1. I don't care about the timestamp for this program. And then let's go into my dictionary called houses, plural, index into it at the house location by its name, and increment that 0 to 1. And now, at the end of this block of code, that has the effect of iterating over every line of the file, updating my dictionary in 4 different places based on whether someone typed Gryffindor or Slytherin or anything else. And notice that I'm using the name of the house to index into my dictionary to essentially go up to this little cheat sheet and change the 0 to a 1, the 1 to a 2, the 2 to a 3, instead of having like 4 separate variables, which would just be much more annoying to maintain. Down at the bottom, let's just print out the results. For each house in those houses, iterating over the keys they're in by default in Python, let's go ahead and print out an f string that says the current house has the current count, and count will be the result of indexing into houses for that given house. And let me close my quote. So let's run this to summarize the data. Hogwarts.py, 140 of you answered Gryffindor, 54 Hufflepuff, 72 Ravenclaw, and 80 of you Slytherin. And that's just my now way of code. And this is, oh my God, so much easier than C to actually analyze data in this way. And one of the reasons that Python's so popular for data science and analytics more generally is that it's actually really easy to manipulate data and run analytics like this. And let me clean this up slightly. It's a little annoying that I just have to know and trust that the house name is in bracket 1 and timestamp is in bracket 0. Let's clean this up. There's something called a dictionary reader in the CSV library that I can use instead. Capital D, capital R. This means I can throw away this next thing, because what a dictionary reader does is it still returns to me every row from the file, one after the other. But it doesn't just give me a list of size 2 representing each row. It gives me a dictionary. And it uses as the keys in that dictionary timestamp and house for every row in the file, which is just to say it makes my code a little more readable, because instead of doing this little trickery, bracket 1, I can say, quote unquote, bracket house with a capital H because it's capitalized in the Google form itself. So the code now is just minorly different, but it's way more resilient, especially if I'm using Google Spreadsheets and I'm moving the columns around or doing something like that where the numbers might get messed up. Now I can run this on Hogwarts.py again, and I get the same answers, but I now don't have to worry about where those individual columns are. All right. Any questions on those capabilities there? That's a teaser of sorts for what some of the manipulation we'll do in PSET 6. All right, so some final examples and flair to intrigue with what you can do with Python. I'm going to actually switch over to a terminal window on my own Mac so that I can actually use audio a little more effectively. So here's just a terminal window on Mac OS. I, before class, have pre-installed some additional Python libraries that won't really work in VS Code in the cloud because they require audio that the browser won't necessarily support. But I'm going to go ahead and write an example here that involves writing a speech-based program that actually does something with speech. And I'm going to go ahead and import a library that, again, I pre-installed called Python text-to-speech. And I'm going to go ahead and, per its documentation, give myself a speech engine by using that library's init function for initialize. I'm then going to use this engine's say function to do something fun like hello world. And then I'm going to go ahead and tell this engine to run and wait while it says those words. All right, I'm going to save this file. I'm not using VS Code at the moment. I'm using another popular program that we used in CS50 back in my day called Vim, which is a command line program that's just in this black and white window. Let me go ahead now and run Python of speech.py and
hello world.
all right, so it's a little computerized, but it is speech that has been synthesized from this example. Let's change it a little bit to be more interesting. Let's do something like this. Let's ask the user for their name, like what's your name, question mark. And then let's use a little f string and say not hello world, but hello to that person's name. Let me save my file, run Python of speech.py, enter. David.
Hello, David.
All right, so we pronounce my name OK. Might struggle with different names depending on the phonetics, but that one seemed to be OK. Let's do something else with Python using similarly just a few lines of code. Let me go into today's examples. And I'm going to go into a folder called a folder called faces.py. Sorry, faces. And in this folder that I've written in advance are a few files. detect.py, recognize.py, and two photos, office.jpg and toby.jpg, if you're familiar with the show. Here, for instance, is the cast photo from the office here. So here's a photo as input. Suppose I want to do something very Facebook style where I want to analyze all of the faces or detect all of the faces in there. Well, let me go ahead and show you a program I wrote in advance. That's not terribly long. Much of it is actually comments, but let's see what I'm doing. I'm importing the pillow library, again, to get access to images. I'm importing a library called face recognition, which I downloaded and installed in advance, but it does what it says. According to its documentation, you go into that library, and you call a function called load image file to load something like office.jpg. And then you can use a line of code like this. Call a function called face locations, passing the images input, and you get back a list of all of the faces in the image. And then down here, a for loop that iterates over all of those face locations. And inside of this loop, I just do a bit of trickery. I figure out the top, right, bottom, and left corners of those locations. And then using these lines of code here, I'm using that image library to just draw a box, essentially. And the code looks cryptic. Honestly, I would have to look this up to write it again. But per the documentation, this just draws a nice little box around the image. So let me go ahead and zoom out here and run this now on office.jpg. All right. It's analyzing, and you can see in the sidebar here, here's the original. And here is every face that my, 10 lines of Python code found within that file. What's a face? Presumably the library is looking for something maybe without a mask that has two eyes, a nose, and a mouth in some kind of arrangement, some kind of pattern. So it would seem pretty reliable, at least on these fairly easy to read faces here. But what if we want to look for someone specific, for instance, someone that's always getting picked on? Well, we could do something like this. Recognize.py, which is taking two files as input. That image and the image of one person in particular. And if you're trying to find Toby in a crowd, here I conflated the program. Sorry, this is the version that draws a box around the given face. Here we have Toby as identified. Why? Because that program, recognize.py, has a few more lines of code. But long story short, it additionally loads as input toby.jpg in order to recognize that specific face. And that specific face is a completely different photo, but it looks similar enough to the person that it all worked out OK. Let's do one other that's a little sensitive to microphones. Let me go into, how about my listen folder here, which is available online too. And let's just run Python of listen0.py. I'm going to type in like David. Oh, sorry. No, I'm going to hello world. Oh, no, that's the wrong version. OK, I look like an idiot. OK, hello. There we go. Hello to you too. And if I say goodbye, I'm talking to my laptop like an idiot. OK. Now it's detecting what I'm saying here. So this first version of the program is just using some relatively simple if, elif. And it's just asking for input, forcing it to lowercase. And that was my mistake with the first example. And then I'm just checking. Is hello in the user's words? Is how are you in the user's words? Didn't see that, but it's there. Is goodbye in the user's words? Now let's do a cooler version using a library just by looking at the effect. Python of listen1.py. Hello world. Let's do version 2 of this that uses a speech-to-text library. Hello, world. How are you? My name is David. No. Is that supposed to happen? Wait. Oh, yes. Hello, world. How are you? OK, that's a bug. OK, let me just do it right. Wait, let's pretend that never happened. Hello, world. OK, so now it's artificial intelligence. Now let's do something a little more interesting, the third version of this program that actually analyzes the words that are said. Hello, world. My name is David. How are you? OK, so that time it not only analyzed what I said, but it plucked my name out of it. Let's do two final examples. This one will generate a QR code. Let me go ahead and write a program called qr.py that very simply does this. Let me import a library called OS. Let me import a library called QR code. Let me grab an image here that's qrcode.make. And let me give you like the URL of like a lecture video on YouTube or something like that. With this ID, let me just type this so I don't get it wrong. OK, so if I now use this URL here of a video on YouTube, making sure I haven't made any typos, I'm now going to go ahead and do 2 lines of code in Python. I'm going to first save that as a file called qr.png, which is a 2-dimensional barcode, a QR code. And indeed, I'm going to use this format. And I'm going to use the os.system library to open qr.png automatically. And if you'd like to take out your phone at this point, you can see the result of my barcode that's just been dynamically generated. Hopefully from afar that will scan. And I think that's an appropriate line to end on. So that's it for CS50. We will see you next time.